Back everyone, and let's begin our session for the second day. This is day 2 as a red color. Maybe red is okay, I don't know. Okay, it still doesn't work. Okay, that's very strange. Okay, this now works. Yeah, so now we have day 2 for the part 1 session. So yesterday we did till question number 7, was that correct? Yes? Question number 7. So you can do, and we'll follow the same rule as yesterday. Thumbs up if you understand, down if you don't, and raise hand if you have any questions, right? So, okay. So let's start with maybe question number 8 then. So we'll try to finish more questions today, but also discuss more concepts today. So maybe introduce some new ideas, some new topic, and see how that relates to what we're doing. So question number 8 was, how many times you write the digit 5 when writing numbers from 1 to 1000. So you write the numbers 1, 2, 3, 4, 9, 10, 11, 12, 100, 101, 99, 100, 101, 999, 1000. So you write all of them together. And how many times have you written 5 if you do this? So anybody solve this? Yes?
So we can first, so we can do it with the freedom of problem solutions. In this we can do like first take out how many times 5 is written in the ones place. That we can take out like first when we see 5 in first 100 numbers, it comes 10 times.
Yes.
For 1000 numbers, it will come 100 times.
Yes.
As ones digit.
Yes, that's
In
correct.
tens digit, it will come again 10 times in the in 1 to 100.
Yes.
So again 10 times 10 times 10 is 100, 100 plus 100, 200, and one time has in the hundreds place has 500.
Yes.
So
Okay.
200.
So sorry, so which one?
201.
So you did everything correct until the last step. So last step there is still more to be done there. Almost everything was correct there. Yes. Yeah? Go ahead.
I have a other solution for this. So first we find it like from 1 to 48 to 49, which would be 5.
Right.
Then afterwards we have 10 more, 15, and then again I think we have 65, 75, 85, and 95 more, which would result in 19. So if every like from 1 to 100 if there are 19, from 1 to 499, there would probably be like basically 90 into 4, which would be.
Okay, let's see. So how did you get the 19? So you're saying 19. So how did you get this? So you get.
So basically 5, 15, 25, 35, 45, then from 50 to 59.
Yeah. 50, 51, 59,
Yeah.
65, 75, 85,
95.
95. So let's count this. Let's count this first, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. It's 20 from here. Because 5 comes twice, right? So 55. That's kind of what I wanted you to be careful about. 55, you have 2 5s there. So try to see where that is going. So try to extend your logic using this idea. See what happens.
Then from 1 to 490, right? That means that we'll have 80 because like 4 times.
Okay.
And then afterwards we have 100 from 500. Then 100, but then there are some
which are
500 digits.
yes.
So those would be 5, 505, 515, 525, 535,
Yes.
545,
Yes.
then 550 to 559,
Yes.
then 565, and so on.
Yes, but even there you have to be careful because 555 has 3 of them.
It has
3. So you have to be careful there, and that's the only last part to be careful about. So I agree that if you do this correctly and very carefully, you will get the correct answer. So this is a correct approach. But yeah. Any other approaches? Yeah.
We know that from 1 to 10 there will be 1 5.
Yes.
So we can times it by 10 to get to 100, which will gives us a 10 5. Then we can add 10 5 for a 50 line, right? That gives us 20. We can again times that by 10 to give us from 1 to 1000, not including the 500 line, and add 100 more for the 500 line.
Okay.
So we can basically keep on multiplying by 10 and adding, 1000 or 10,000 like that.
Yeah, that makes sense. Okay. So you can kind of like build small cases and build there by just adding a 0 next to it and then working those lines. Yeah.
Sir, as we know from 1 to 100 there are 20, so we can directly multiply it by 10, which gives us 1000.
And 20 and 10, so 200, right?
Yeah. So from 1000 it will be 200, and as we know that from 500 to 599 there are 105, so we can just add it to the 200, which is gives us 300.
Fair. So you can do that as well. Okay. So what do you get as the final answer? 300. Okay. So because you're adding all the 500 to, so that's correct. So 300 would be the answer. So this works out, right? So all of these approaches, if you do them carefully, will give you the answer. But let's try to do something which does not require doing all the cases. Let's try to do something very quick, where you don't have to be careful about the 555 and all this, right? So if you just look at these 3 boxes, well, how many cases are there where there's only 5 over here? So how many such numbers are there where 5 is the last digit? And other 2 you can choose from 0 to 9. Right, so you can have leading zeros. So you can have 005 can be your 5, and that wouldn't affect anything. So adding zeros in front of a number does not affect anything, right? So for example, if I had 57, even if I write it as 057, I'm counting the same number of 5s. Like that does not affect anything, right? So you can do it this way. Yeah. So you can think of this as going from 0 to 9. You can think of this as going from 0 to 9. Everybody okay with this so far? So if I just add a 0 to everything, let's say I had number 65, I made it 065, number of 5s has not changed. I can just add a 0 behind it, right? Even if there was just a number 7, I make it 007, this number of 5s has not changed, right? So I can always add these zeros next to them, right? So you have these 3 things, and you can choose digits from 0 to 9, 0 to 9. How many ways are there of choosing these 2 digits? Yeah?
700.
Not 700, right? You have 10 choices for this one and 10 for this one. So how would you get if you're picking pairs from 10 and 10? 100, right? So for example, if you have fix a 0 here, there's 10 cases. Fix a 1, there's 10 cases. Fix a 2, there's 10 cases. So for all of them, there's 10 cases, and there's 10 possibilities to choose from. So it's 10 into 10, 100 cases, right? So 100 cases like this. Everybody okay with this? So you counted these types of 5s 100 times. There's other types of 5s as well, right? So say 5 was in the middle. Yeah?
There would still be 100 cases.
Exactly. There will still be 100 cases because you're 0 to 9. You're 0 to 9. There will still be 100 cases, right? By the same logic. 10 into 10. So 10 choices here, 10 choices here. For every digit here, there's 10 possible cases, and you have 10 choices total. What if 5 was in the leading place?
So the same will happen.
Same will happen, right? So everybody agrees same will happen. So there's 100 cases again. But notice that every 5 which could have occurred in your thing, in your big number, 1, 2, 3 till 1000, every 5 which could have occurred is one of these 3 possibilities. There's no other way you can get a 5, right? And even if it is a repeated 5, even if it is something like 455, let's say, both of these 5s have been counted. One time you have counted this 5 using this one time you have counted this one using this one, right? So all 5s have been counted by doing this approach. So you're not missing anything, and you're not extra counting in any way, right? Everything is in place. So you have 100 plus 100 plus 100, so that's 300 cases. So there's a total of 300 times this appears. And if you're not convinced, if there's any questions, you can always use a computer to verify, right? So we can just quickly verify this in a computer code. Let me see if I have PyCharm. and I can show you later after class if you want. You can come here. I can show you the code which tells you exactly how many there are. Just like prints this instantly. So it's not a very difficult algorithm, but you can always verify this. Yeah. Okay. Everybody good with this? Everybody follows? Thumbs up? Thumbs down? Yeah. Okay. So let's move on to maybe question number 9 then. So where is question number 9? I forget the question. Similar type of question, but more funnier. So you have numbers from 1 to 1000. How many of them have the units digit from 2, 4, 6, 8 and 5? So units digit is this. We don't care about the tens and hundreds digit. So this is tens, this is hundreds. We don't care about them. We just care about the units digit, right? How many of them have a units digit which is 1 of 2, 4, 6, 8, 5? Yeah?
I think it's 100 cases like we did for the previous question.
Okay, so we have 10 into 10. But then what about these? There's 5 choices here, right?
So you multiply that
By 5, exactly. So,
another 100 cases for each.
yes, so you get like 500 total, right? Because you have, so this one can take values from 0 to 9. This one can take values from 0 to 9. And then you have 5 choices for this one. So for every choice here, there is 10 cases and 5 cases there. So there is 10 into 5, right? Because every time I fix digits, let's say 1 and 3, there's 5 possibilities. So for every pair of digits, there's 5 possibilities. And then how many pairs are there? So we counted that earlier, that was 100. So it's 500, right? So that will give you the answer very quickly. That's one way of solving the problem, right? So this is one approach of solving the problem. I wanted to show other approaches as well. So this is the quickest way of doing it. But sometimes the long way can also teach you new ideas, right? So even if you do it in a long way, maybe that idea is useful in some other place. So we'll try to do this long way. But is everybody okay with this approach? Yeah? Everybody okay with this approach? Great. So let's try to do this the long way. When you look at the units digit, does that remind you of something? Like when do you look at units digit of a number? So when I have a big number, let's say 1754553, when do you look at this digit at the end? Like is there a particular instance you look at it?
When you want to just divisible by 2.
Divisible by 2? And?
Divisible by 10 and 5.
Yeah, so divisible by 2, by 5 or by 10. Like this is one common reason to look at the units digit, right? So any number which ends in 2, 4, 6, 8 is a multiple of 2. It's even. Ends in 5 is a multiple of 5.
0 is also a multiple of
Yes, but here we are not allowing 0, right? So here we only want 1, 2, 4, 6, 8, 5. So here we don't want 0. So but that's a good point. All the even numbers will be given to you if you had 0, 2, 4, 6, 8 and all the multiples of 5. I hope my handwriting is not too bad. 0 and 5, right? And if a number ends in 0, that's a multiple of 10. Right? If it ends in 0, it's a multiple of 10. Everybody good with this? So let us count the number of even numbers from 1 to 1000. Half of them, right? So it's like if you're counting from 1 to 1000, half the numbers are even, half the numbers are odd, right? Yeah?
So we can indirectly say that that it just wants us to find the number that is divisible by 2 and 5 but is not divisible by 10.
Exactly. So this is the formulation I was looking for. So we want numbers divisible by 2 or by 5 but not by 10. Make sense? So if a number is divisible by 2, it will be 0, 2, 4, 6, 8 at the end. If it's divisible by 5, it will be 0, 5 at the end. But if it is not divisible by 10, there won't be 0 at the end. So it will be our type of number, exactly the kind of thing we are looking for, right? So we have changed the question into finding all numbers from 1 to 1000 which have this property, right? Everybody good with this? Now let's try to draw some pictures. So let's say this is all multiples of 2. And let's say this is all multiples of 5. All the multiples of 10 are in the middle, right? Like these are the ones which are multiples of 10 because being a multiple of 10 is same as being a multiple of both 2 and 5.
So considering the topic of sets, basically find how many numbers are divisible by 2, how many numbers are divisible by 5, add them and subtract them by 2 times the
Yes.
numbers that are divisible by 10.
Yes, correct. So does everybody follow this logic that let's say these are numbers divisible by 2, these by 5, then the only ones divisible by 10 are the ones in this intersection, in this middle, right? Everybody good with that logic? So when I add this size plus this size, I'm counting this particular region twice. Like I'm adding this particular piece twice, right? So it's like if I add these two cakes together, this particular common intersection is added twice, but I don't want it any number of times. I don't want this at all, right? Like you want to, in some sense, do the dotted area, not the shaded area. That's kind of what you want to find, right? So what's the total number of things divisible by 2?
500. And for 5 it is 200. And for 10 it is 100.
Exactly. So 5.
500 plus 200 minus 2 times 100.
Exactly. So you have this, which is 500, because half the numbers are odd, half the numbers are even, right? So it's 500. This, which is 200, because how many are divisible by 5? 5, 10, and so on till 1000. So 1000 is 5 times 200. So you get 200 minus, you're subtracting this 2 times. How many are in common? Divisible by 10? 10, 20 till 10 times 100. So 100. So this again is 500. Yeah? Everybody good with this approach? This is a pretty important way of looking at the picture. It's called the sort of principle of inclusion and exclusion. And it's one of those cases where, although this method is longer, it takes more time to find this type of thing in exam. It is a much more general method. Like you can solve many more problems with this method than just the previous method of like, oh, you got 100, 100, 100 and so on. So this is a different method, but it's more general. Yeah.
So if you just wanted to solve this like quickly,
Mhm.
we could just say that between 1 and 10 there are 5 of these digits.
Mhm.
So you can directly multiply it by
Yes.
100 and get the answer.
Exactly. That's the quick approach. The quick approach is this, yeah. Just 10, 10 and 5, that's 500. The point of doing it this way is that this is not a quick approach, but this is a more useful approach. You'll see many more problems where this is the more reasonable thing to do than what we did earlier. For example, if you want replace 5 by 7 and this by 14, for example, now it's very unclear. Now it's not very easy to solve using the previous method, but now this method still works. You still have to do the exact same type of thing, right? So this is a more general method, whereas that one is more specific to property about digits, right? So everybody good with this? Thumbs up, thumbs down? Yeah, any questions, feel free to ask at any point. Yeah? Okay, so that's question number 9. Then we can move on to maybe question number 10. And this one is interesting. So there's a funny operation. There's a strange operation. There's a diamond. So normally you have a plus or a multiply, but we have a diamond here and it does this. Does this thing, right? And you were supposed to find, I think, the value of 2, star 3, diamond 3, diamond 4. So what did people get when they solved this?
So there was also diamond 5.
Oh no, that is, I think, is it diamond? This is, I think, part 1. There's only diamond 4. There's diamond 5 in, I think, part 2. But yeah, they are this. Yeah. So what was the answer you ended up getting by doing this calculation, if you remember by any chance? It's not a very memorable answer, but it's a slightly memorable answer. Like you will remember. 119, right? So I won't do the calculation. You just have to do this many times, and you'll find the answer. Right? So that's one way of doing it. And if you've not seen this before, I'll mention another thing. If you change the order, let's say you change it, you make it 2, 1, 4, 3, and then you put the diamonds in the middle. What will you get then?
So the same answer.
Same answer? Yeah. That's a good guess. And no matter which order you do this in, you'll end up getting the same answer. So that should be a little surprising, right? There must be something going on, yeah?
So it is because multiplication and addition is commutative.
Yes, but this is neither multiplication or addition, right? So if
So it's A into B and A plus B, it contains both multiplication.
no, but think about this, right? So if I replace this with AB plus 2 times A plus B, then you can check it won't be commutative, like it won't be something which commutes. So there's something special about what's going on here, right? So, okay, if it was just AB, then of course I agree. It's like 1 into 2 into 3 into 4. That's easy. If it's just A plus B, you just add all of them. So then order does not matter. But for this operation also the order does not matter, which is somewhat surprising. It should at least be a little surprising why this happens.
So the order matters because there are brackets.
There, sorry, which ones? Sorry, can you repeat?
So the order matters because the bonus is being used, there are brackets.
Oh, there are brackets, yes. No, but I'm saying if you do 1, 2, 3, 4, this versus if you do 4, 3, 2, 1, you'll get the same number at the end. And even if you replace this 4, 3, 2, 1 with any other order, you'll get the same number, the exact same number every time you do this. Yeah?
I think this is because this is actually only multiplication.
Hmm?
It's like A into B plus 1.
Mm-hmm.
Here B is actually in bracket with 1 and B into bracket A plus 1.
Close, but then you're getting something extra. Like think about that, right? So it's like this is close, but you're getting something extra. So that's the right spirit of the idea, that this should essentially be multiplication. Like this operation is not different enough from multiplication where that will be a problem, right? That's kind of the idea, that it should be essentially multiplication. But how do you check that? So let's try to do it for small cases. Yeah, I mean you've seen this, so you don't speak there. But yeah, is everybody okay with variables? Like, is everybody comfortable with ABC, algebra? Everybody good with this? Like, thumbs up if you're good with it, thumbs down if you're not good with it. Okay, so if you're good with variables, then let's try doing A star B or A diamond B, diamond C. Let's try finding what this value is, and maybe that will be a hint for what's going on, right? So A diamond B is AB plus A plus B. So when you do A diamond B, diamond C, so AB plus A plus B, whole number is something. Like if this number is X, this is X, C plus X plus C, right? Make sense? Everybody good with this over there?
So C plus X plus C.
So X times C plus X plus C, where X is this one. Just because we are using A star B, A diamond B as X. We are using this one as X. So this is AB plus A plus B multiplied by C is ABC plus AC plus BC. This one, now you pull back, is AB plus A plus B plus C. So when you rewrite, you get ABC, AB plus BC plus CA plus A plus B plus C. That is interesting, right? That is interesting because it is completely symmetric in ABC. So even if you change A and B with each other, you'll get the exact same thing at the end, right? So for example, if I flip A and B, this one is same. Flip A and B, this one is same. These two switch with each other, right? And then this one is the same. So if I change A and B, nothing changes. Which means if instead of 1, 2, 3, I do 2, 1, 3, I'll get the same number. Because this one is completely symmetric, right? And that's kind of how it will happen for every pair. So even if you change B and C, or even if you change C and A, you'll end up getting the same thing. So what you can see is that all 6 possible arrangements, you'll get the exact same value at the end. So this is especially an important topic, and it's called symmetric polynomials. So you'll learn this maybe later, but not necessarily in school, but maybe outside. And this is a very crucial topic. It's a very important way of understanding polynomials which have this property. So you'll learn this maybe at some point later, but let's try to do the plus 1 idea. You had an idea about making it A plus 1, B plus 1 somewhere, right? So let's try to see what that idea looks like. So yeah, AB plus A plus B. If I add a plus 1 and a minus 1, because what I'm trying to do is A times B plus 1 plus B, right? So it's A times B plus 1 plus B. Yeah? If there is only a plus 1 here, I would be able to factorize. Right? I'll be able to make this a product of two things. So I'll add a plus 1 here. Let's say this is X, then X plus 1, A times B plus 1 plus B plus 1, and then you get A plus 1 times B plus 1. Yeah? So if you add 1, you get this. So X is equal to 1 plus A, 1 plus B, minus 1, right? Which means that this is what A diamond B does. It takes 1 plus A, 1 plus B, multiplies them and removes 1. That's what A diamond B is as an operation. So if I do A diamond B, diamond C, and I call this one X, I'm doing 1 plus X, 1 plus C, minus 1, right? Now 1 plus X, when you have X here, and you bring the 1 here, is 1 plus A into 1 plus B. So this is 1 plus A, 1 plus B, 1 plus C, minus 1. Make sense? What that means is if you do any number of these operations, so I do 4, 5, 6 of them, let's say I won't put any parentheses, but I hope it's clear what the order of brackets is. Let's say I do something like this. This is just going to be 1 plus A, 1 plus B, 1 plus C, 1 plus D, 1 plus E, minus 1. And you don't care about what the order is now because this product is going to be the same. So even if you change A, B, C, D, E in any order, the product of them is going to be the same, right? 1 plus A, 1 plus B, 1 plus C, 1 plus D, 1 plus E. This will be the same no matter how you change them. And so when you go back to your original question with 1, 2, 3, 4, what you're doing is 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, minus 1. So that's 2 into 3 into 4 into 5. Oh no, this is what it turns out to be. We're not adding it sort of out of our own will. It's like this is what happens if you look at the operation, right? So if you go back, this was just the two numbers case, A, B, and you had AB plus A plus B. I wrote this as A times B plus 1 plus B because you had the idea that we were making it B plus 1, right? If only there was one more plus 1 here, we would be able to factorize it. We would be able to take B plus 1 in common. So I added plus 1 and then I made it B plus 1 forcefully. And now we take B plus 1 in common. So you have A plus 1 into B plus 1, right? So you have X plus 1 is A plus 1 B plus 1. So X, which is the A diamond B, this is X, is 1 plus A into 1 plus B minus 1, right? All good? Now if I did the A diamond B, diamond with C, I'll get 1 plus X into 1 plus C minus 1 by this above expression, right? Because if I do A diamond B, I get 1 plus A, 1 plus B minus 1. So if I do X diamond C, I'll get 1 plus X, 1 plus C minus 1. Same formula, right? And 1 plus X you can put back 1 plus A, 1 plus B. So you get 1 plus A, 1 plus B, 1 plus C minus 1, right? And you can use the same logic. You can keep doing the same logic and you end up in this place. Keep doing the same logic, you'll end up with this. So if you have 1, 2, 3, 4, this is what the final answer will become. It will be 120 minus 1. So you get 119. But this logic is very powerful because now you have a full formula at the end. So even if you had 1, 2, 3, 4, 5 in the diamonds, you'll end up getting 2 into 3 into 4 into 5 into 6 minus 1, 720 minus 1, which is 719 in that case. So now you can solve this question for any number of n. You don't just need to restrict to 4. You can solve it for 5, 6, 7, any number, and it will be 1 minus a factorial. So I don't know if how many people have seen the word factorial before? Maybe we discussed it yesterday. Seen factorial, right? So this is the final answer for something like 1, diamond 2, diamond 3, diamond n is going to be n plus 1 factorial minus 1. So this is going to be a general formula, and now you can solve this question for any value of n. So the question was designed where during the exam, if you're just doing 1, 2, 3, 4, you should be able to do by hand. Like 1, 2, 3, 4 is not that difficult by hand. You should be able to find the answer. But if you're thinking about this after exam, maybe you realize that there's a formula, that there's a pattern to it, right? So that's kind of the intent of this question. Everybody good with this? Everybody good? Okay, let's try next one. So this was question 10. Now let's do question 11, which I think is a bit simpler. So it's a bit of an easier one in some sense. Let's say my number x is 1, 2, 3, 4, 9, 8, 9, 10, 11, 99, 100, 101, 129. So how many digits are there in this number? So how did people solve this? Think about it. Yeah?
So we'll first take out like till 1 to 9.
Okay.
So 1 to 9.
That's,
There are 9 digits.
yeah,
Because 1 digit number.
yeah.
And from 10 to 99,
Mm-hmm.
there are 2 digits. So 290, so 180.
Yeah.
80
Okay.
plus
Yeah.
20, 30 into 3.
Yeah.
90 plus 180, which is 270, 279.
Yeah. 279, right? And yeah. Yeah, so you end up at 279, and that's, yeah. So this was a more simpler question. So just to see if you're counting very simple things after doing like very complicated counting, you're doing more simple counting. Is everybody okay with the logic here? It's just like 1-digit numbers, 2-digit numbers, 3-digit numbers. You count how many there are, multiply them with the number of digits, and just add all of this, right? It's also the number of pages in the book, so I thought it's a funny answer to have at the end. Yeah. So yeah, this one is a bit simpler. But everybody okay with the previous one? Okay. So then we can go on for question 12. Now we are getting more into the logic type of questions, not so much numbers, more so just logic and thinking. And so if you found the answer, so the next question is something where if you know the answer or if you found the answer in test, you should not raise your hand or spoil the answer. But if others have not thought about it, think about this, right? So you are in a place with knights and knaves. And so I'll just call them truth tellers and liars, right? Because T and L is easier to say than K and K because you don't know which K is which. Knave is someone who's a liar. So yeah, I'll just say liars. I'll use L, and truth teller. So that's T. I'll use T for knights, right? So that's a yeah. Oh yeah. First, let me get the question out, then you can answer.
I remember the question that everyone said the
Yes.
other that you are all knaves.
Yes.
The answer should be there should be one knight on the island, because if the knight will say to the knaves that you are all knaves, so essentially it will be true. And if the knaves say to everyone that you are all knaves, then the knight and the knight on the island will make the knave statement false and a lie.
Yes. So that is the correct reasoning.
There
Yes.
should be one knight
Yes.
on the island.
Yes. Yes. Yes.
Although this was not mentioned in the question originally, so there should also be one knave as well, because if they told everybody that you are all knaves, and if there were multiple knaves, then that would mean that if they told the knaves that they were knaves, that they would be telling the truth.
No, then that's slightly. That is possible. Yeah.
We are given the
Yes.
people on the island.
So you can have like one knight and any number of knaves, because for every knave the statement will be all of you are knaves. That statement is false, right? Because it's not saying individually. No, it's just saying one statement about all of them. So you have to be careful there. So the point of this question is that, okay, I think everybody has the answer now, but point is to think about the logic and how you come up with a proof of this type of thing, right? So let's go here. Let's try to understand what's going on there. So you have one truth teller, or maybe they have like some number of truth tellers, and then you have some number of liars, right? So there's a bunch of T's and a bunch of L's, and everyone says all of you are liars. Now, if all of them actually are liars, let's say there's no truth tellers out there, if all of them are liars, that's a true statement, right? So then everyone who's a liar is saying a true statement, which cannot happen. So 0 T's is impossible. If there's no truth tellers, then everybody's statements become true, right? Because everybody's saying all of you are liars, and they are all liars. So then they're all saying the true statement, which can't happen, right? So 0 T's is impossible. And it's kind of like you're arriving at a contradiction. You're starting with your assumption that 0 T's are there, and then you end up in a contradiction. So you have to be careful with this. Then you can't have 0 truth tellers. What about 2 truth tellers? So if you have T1 and T2, and you have rest of them who are liars or whatever, is this still possible? No? Yeah? Yes, because when T1 says all of you are liars, T1 means T2 is also a liar. But that's false. So T1 statement is false, right? So T1 statement is false, which can't happen because T1 is a truth teller. The important thing, which as you mentioned is a subtle point here, is that when you say statement of the form all of has property, when you make a statement like this, right, what does it mean for the statement to be false? Is that any one of them does not have the property. So it's not like, so when I say all of you are in 5th, 6th or 7th, the only way that statement is false is if one of you, any one of you, is not in these 3 classes, right? So you don't need to. I don't need to be wrong about all of you, or every single one of you. I just need to be wrong about one of you for the all statement to be false. And that's an important thing to understand. Is that when you say all of something is false, it's like okay, it means that there exists one of them which does not have the property. So here, because T2 does not have the property that T2 is a liar, T1 statement becomes false, and similarly T2 statement becomes false. So both of these, so more than 2, yeah, is also not possible. Now, why do I say greater or equal to 2? If there was only T1 and T2, I've only proven that 2 truth tellers is impossible. Maybe 3 is possible. Maybe 4 is possible. When I say greater or equals 2 is impossible, I have ruled out all of those cases. Because if I just have 2 of them, that alone is enough to get a contradiction. So if you're doing this properly, you have to be very careful. You have to say that, oh, greater or equals 2 is impossible, not just 2 is impossible. Because then 3 could be possible, 4 could be possible. You have to make the reasoning precise there, right? That it is impossible for any number more than 1. So the only possibility is one truth teller. Yeah. Now you still have something to do. Although you have solved the question, you can write 1 and then you get your marks in the question. You still have something to do as far as the proof is concerned, right? Because it can happen that just like greater or equals 2 is impossible, just like 0 is impossible, maybe 1 is also impossible. Maybe 1 is and the whole question is impossible completely, right? So you want to rule out that possibility as well, that 1 is actually possible. So you want to make the claim that it is possible to have one truth teller and any number of liars, right? In that case, you can just pick up any configuration where one truth teller is there, some number of liars are there, and the problem condition is satisfied. So you don't care about the precise number, you just need to show one example is possible in this case, right? And what's the one example? Well, if I have one truth teller and let's say 2 liars, let's say, when everyone says all of you are liars, this statement is false because there's a truth teller, this statement is false because there's a truth teller, and this statement is true because both of them are liars. Right? So then everything is consistent. If you don't check this, then also your proof is not complete in some sense, right? Because it could happen that maybe even 1 is impossible, and then the problem itself makes no sense. But here the problem does make sense. There's one case where you have checked that this can actually happen, and every other case with different number of t's cannot happen. Yeah?
So I had a question, but like if a liar tells to a liar that you are a liar,
Mm-hmm.
what will happen in that case?
Okay, if it's just a liar and liar, that can't happen, right? So if a liar says you are a liar, that's a true statement, and a liar will never make a true statement.
But when there is a one truth teller, so like one liar will have to tell to both of them.
Oh no, so he's not. So that's an important clarification. You're not telling to each of them individually. You're telling to all of them at once. So I'm saying all of you are liars, right? Instead of pointing at you, pointing at him, pointing at her, that kind of thing. I'm saying all of you are liars. That's the statement being made. So for my statement to be wrong, just one of you needs to be a truth teller. If one of you tells the truth, then my statement is wrong, right? So it's that sort of idea. And of course, if it's only 2 liars, then this is inconsistent. Inconsistent, which means that this kind of situation is impossible. Like they're breaking some rule if that's the case. That's what I meant, that you have to actually check that one truth teller is possible. Maybe that case was also inconsistent. So you have to make sure that that case is possible, right? Sometimes these questions have this funny thing where all statements are inconsistent, and that is also one of the options sometimes. But there's no options here, so you know one is the answer. But if there are options, then this is a possibility that all of them are inconsistent. Okay. For example, if X says, I am a liar, and X is either a truth teller or a liar, this statement is inconsistent. It cannot happen, right? Exactly. Yeah. Still, he has to say he's a knight. Exactly. Exactly. So when let's say X is a truth teller and X says I am a liar, that can't happen. Right? Someone who's a truth teller will not say I am a liar because they will say the truth, which is that they are a truth teller. Right? So someone who's a truth teller will say that I am a truth teller. Somebody who's a liar will not admit they're a liar because that will be a true statement. So they will lie and say I am not a liar, I am a truth teller. So in both cases, this is an impossible statement, right? There's all kinds of puzzles, right? So you can ask one person what the other person will say. You can ask the person what they will say about themselves. There's all kinds of puzzles with this. Yeah.
Sir, the reason that one night on the island is correct just prove to us 2 or more knights will not be possible.
Exactly, exactly.
One knight will make all the knaves statement false, and the
Yeah, exactly.
statement will basically be true.
Exactly, exactly.
And he tells all the knaves that you are all knaves.
Yes, exactly. So that is the point. Is that zero truth tellers, 0 knights is impossible. Greater equals 2 is impossible, and in 1 there's actually a possibility where everything is consistent. That is the complete argument. Yes.
So will there always be one truth teller on the island?
There'll always be one truth teller based on these conditions, and exactly one. You don't, in some sense, need a liar in a way, but that's a more sort of pedantic thing. If you only have one truth teller and 0 liars, right? And he just shouts to nobody, all of you are liars, that's still a true statement because you can't disprove his statement. You can't say that, oh, I know somebody here who's a truth teller. That's still a true statement, but it's the kind of statement which is a vacuously true statement. So it's true because there is no content to the statement, right? For example, if there's nobody in the room and I say all of you are truth tellers, that's still a true statement because you can't find a liar in the room for me, right, to disprove my statement. So it's a sort of vacuously true statement. Yeah?
Sir, what did you mean by vacuously true?
So this is precisely statements of the form where, okay, there's no, okay, if I say all prime numbers, all even prime numbers greater than 2 are squares. So if I say all even prime numbers greater than 2 are squares, if I make this statement, it's a very ridiculous statement, right? Because there's no prime number which is even and bigger than 2. 2 is the only even prime number. So then it is a true statement. So this statement is true because it's not saying anything. It's not saying any concrete thing, right? So to make, so when you say a statement is false, so I say all something has property something else. When I say this statement is false, I have to give an example of something which does not have this property. I can't give an example of an even prime number bigger than 2, which is not a square. Why can't I give that example? Because there is no even prime number greater than 2 in the first place. So how will I give an example? And so these kind of statements are called vacuously true statements. They're true, but they don't mean anything, right? And you can even make them more interesting. So I did this, I think, in one of the talks, but I think it's worth mentioning. So if 1 equals 2, so you can make statements like this as well. If 1 equals 2, then I'm Santa Claus. Yeah, that is one of the talks, right? So the point is that, and there's also a proof of this. So this is not this is a true statement. So very surprisingly, this is a true statement. It does not even matter whether Santa Claus exists or not. The statement is true independently of that, which is very surprising. Yeah, so the main point is that any false statement implies anything else. So if you believe anything false, if one of the things you believe is false, then you can imply anything with that statement, right? And I can give you a proof of this as well. It's not a very difficult proof. If you look at me and Santa Claus, so it's like 2 people here. Well, 2 equals 1, so there must be only 1 person, right? So we are both the same then. So this is a proof. This is not. There's nothing incorrect about this proof because you are assuming something which is false. This is clearly false. So if you are assuming a false thing, then you can prove anything. You can even prove that I am not Santa Claus. And this is also true regardless of whether I exist or Santa Claus exists, or both of us are in fact the same. This second statement will also be true. Why? Because 1 equals 2. So if this was 1 person, then there are 2 people now. So point is that if you have a false statement, you can sort of prove anything, and with a false statement you can prove one statement and the negative of that statement, the opposite of that statement as well. You can prove both of these things if you assume anything false. And so that's, so if it ever happens that you have proven something is true and you have proven P is false, whatever you were using to get here, that must be false. So if you are ever able to prove something is true and something is false at the same time, whatever logic you are using, whatever you are assuming, must be the false one. And this is what gives you something called proof by contradiction. And so this is what gives you proof by contradiction. I think you might not have seen this in school yet because usually they use it to prove that square root 2 is irrational. That's usually one of the classic proofs which uses proof by contradiction. But there's many proofs. You can do many. Everything you did about 0 is impossible, 0 nights is impossible, 2 greater equals 2 is impossible. That's also in some ways a proof by contradiction. Like you're kind of using the same type of logic. Yeah.
Sir, what if you say that if 1 is equal to 2, I will get full marks?
Yeah.
But a question is that 1 is equal to 2, is it true or false?
Mm.
And at that time it is another thing, and when you get full marks it becomes another.
Yeah.
So it's a paradox.
No, it's a paradox in the sense that it's all true statements which don't mean anything. So if you have a true statement which is not saying anything, that's okay, right? It's not a problem. Because what we agree on is that when we want something of this form to be false, you have to give an example. Or at least have to show that there is an example. Maybe you don't show me the exact example, but you tell me there must be an example. If something cannot even happen, then there's no example to disprove it, right? So then it's sort of like, it's true in a very vacuous sense. And that's why these are very interesting, sort of tricky things which happen. I didn't want to include this in the test because that might have caused like some confusion. So, but this is like more after test. But there are questions where there's vacuous truths being involved, right? So there's questions of that sort as well. Yeah, everybody comfortable with this? Thumbs up? Yes? Okay. Okay, so if everybody is thumbs up with this, let's do one more. There's more knights and knaves, right? So this is more knights and knaves. And you have A1, A2, A251, I think. Yeah, they gather together. Yeah.
Is the answer 126?
Yes, 126 is the answer for this. Yeah. So just wait for a bit. We'll discuss. Yeah. Oh, you had something? Okay. Good. Everybody's comfortable with subscripts, right? Like A1, A2, A3. Everybody's comfortable with that sort of notation, right? So A1 says A2 is a liar. I won't use knights and knaves because then the k and k can be confusing. You don't know which one is which. Even it's not even a k and k. Kn is also common, right? So you don't really know at all. You can't use like k and kn. A3 is a liar. All the way till A250 says A251 is a liar. And A251 says something different. So A251. More L's than T's, and more is strictly more, so they cannot be equal as well. Strictly more T's among A1 to A250. So that's the statement A251 makes at the end, which is different from their statement, right? No, we'll get there. Like if you have the answer, if you have the correct answer, then you also have the correct logic. So if your answer is 126, you know what you're doing, right? So it's fine. We'll get there. Yeah. So your question?
Basically, right now there are two possibilities. A1 is either a liar or A1 is either a
Truth teller. Yes.
teller.
Yeah.
In case A1 is a liar, then all odd numbers are liar.
Yes. That's the idea. Yes.
Then wouldn't A251 also be a liar?
Yes. Okay. So, yeah.
So if you notice, if A1 is telling the truth, then A2 will be a liar, and then A2 will be a liar. So so A3 will be a
Exactly.
So that's what he just said.
Yes.
Now it's the same case with that. If A1 is a liar, then A2 will tell truth. A2 will tell truth. So A3 will be.
Yes.
and
Exactly.
So then it would evenly distribute A1 to A250 in equal number of knights and knaves.
Yes.
Proving A251 to be false.
Yes.
And since A251 is telling the false, he is a knave. And since A251 is
Yes.
a knave, A1 is a knave. So
Yes.
there are
Yes.
one more knave than knights at the gathering.
Yes.
So
His statement is correct.
So x plus 1 is equal to 251. So you find.
Okay. So, let's start with this.
If we see that A251 is a knave, then why we are considering his statement as true?
So let's do this systematically so we know what's going on, right? There's too many ideas floating around. So assume A1 is, let's say, one of T or L. So let's start with assume A1 is T. Okay. Then A1 says A2 is a liar.
That will be a true statement.
It's a true statement. So A2 is a liar. Now if A2 is a liar and A2 says A3 is a liar, that's a false statement.
So sir, A2 and minus so A2 so sir A2 and so sir then A2 and minus 1 will become
Yes.
2 and A.
Yes, the odd and even splits, right? So it's like if A3 is telling the truth, then A3 statement A4 is a liar. This becomes true, and so A4 is a liar. So you can keep alternating. A1 is true, A2 is false, A3 is true, A4 is false. This alternates, right? So you get A250 is liar, and A250 was saying A251 is liar. So this is a false statement, which means A251 is telling the truth. But what is A251 saying? A251 is saying that among you guys, among A1 to A250, there is more L than T.
But sir, that statement is false because they are equally distributed.
Yes.
Because they are alternating.
So there's odd and even, and there's in till 250. So there's 125 odd, 125 even. So A251 statement is false.
So sir, A251 becomes a name, and since we given the statement A2 and minus
Yeah, no,
depend on A.
no. So that logic is fine.
We can find the reverse. So A2
No, so
A1 will become a.
no, so that logic is correct. But the point is that this is actually an important point. I want to focus on what's happening here. We assumed so A1 is not true. So A1 must be a liar. Now if we do the logic again, A1 is a liar. Okay, we do this logic again. It can happen that maybe A1 is a liar is also giving a contradiction. That could happen, right? And if that happens, then the problem does not make any sense. If both things are giving a contradiction, that cannot happen. So let's see if this actually makes sense. So A1 is a liar, and A1 says A2 is a liar, implies this is a false statement. So A2 is a truth teller. Now A2 is a truth teller who says A3 is a liar. So that's a true statement, implies A3 is a liar. And you keep alternating like this again, right? So A250 is a truth teller, and A250 is saying A251 is a liar. This is a true statement, which implies A251 is a liar. But we actually need to check whether he's a liar or not. We need to check that last statement, right? And last statement A251 is saying more L than T. But L and T again both are 125, 125. So this is a false statement. So this is a false statement at the end that A251 is making, which means he is a liar. That is correct. So this is consistent.
But wouldn't we also include 251 in this group?
Oh no, he explicitly he's saying among you, among A1 to A250. Otherwise this will flip the coin. But if you include that, then I think you might get contradiction in both cases, which is that's bad, right? So this is a consistent case, and it is the only case. We have ruled out that there is no other possible option. This is the only possible case. And so the answer is how many L's are there? 125 plus this extra one. Right, so this one, so 126. The reason I did this and check the case when A1 is a truth teller, that could also maybe give a different answer. And turns out that A1 being a truth teller is impossible. That just cannot happen. Right, so you need to check both cases.
Sir, so it's not directly like the logic which I used, but I found out that this is related to something which we use in maths also, which is like basically in integers, in multiplication. So a negative integer multiplied by a
Yes.
positive integer means that A1 is like lying, so negative into negative.
Yes, exactly. So this is a very good observation, and it does lead somewhere. So we are about to wrap up, but I'll mention quickly. The truth is somewhat like +1, false is somewhat like -1, and you're multiplying in some ways. That's what you're saying, right? So I won't say much about this, but this is actually correct, and this goes into a much deeper area of logic, which is, you might look it up. It's related to this. You can look up something called Boolean algebra. So it does come up in some ways. Like what you're saying has a deeper meaning in some ways. Like you can sort of use this to develop more maths. Like there's more maths where you're pointing at. So you can search about this, look it up. I won't talk about it because that's a more complicated topic. We are doing something which is more problem solving, but you can always go home, just sort of check it out, find out what's going on there. What you're saying has meaning and relevance there, right? So is everybody comfortable with the discussion we had about this knights and knaves problem? Sounds good. So we'll wrap for today, and then tomorrow we'll finish not just these problems, but also do some more modular arithmetic, because that's where I think we'll need that for next few questions, especially the agents question, for example. We'll need that. Yeah. Any questions? Everybody?
Tonight's question was easier in part 2.
Yeah.
Because we were told that there are more truth tellers than the liars. So it was more easier for us.
Nice, yeah. Yeah, no, I think that the idea of keeping the same question in different parts is sometimes you want to see how, especially because we are research oriented, right? So we want to see how something which is natural for you in 5th, 6th, 7th, maybe it's not natural for you in 5th, 6th, 7th, becomes unnatural when you grow older, or maybe it's like, oh, something was natural before and now it becomes difficult to think about. So we kind of have that analysis figured out on our side. So we are able to use that to come up with better ideas of how to teach that, right? So it's we use, I think there's some questions which are common in all 3 parts, some in 1 and 2, some in 2 and 3. And the idea is to sort of see how that evolves. But yeah, any questions before we wrap up? We'll put a break on the stream for now. Yeah, we have 1 minute. I think there might be there's a message. question number 9 because we did till 8 last time. So you have these sinks. So you have this big pool and then you have these sinks, and they can so this takes 2 hours to empty the tank by itself. This one takes 3 hours. This one takes 100 hours. So you have all these sinks, and so these are sort of like these small pipes, right? And you can only turn on some of them, and you want to empty the whole tank by turning on some combination in less than 40 minutes. Right? You want to do this in less than 40 minutes. So what's the smallest number of these that you have to open? Now you can't repeat it. So there's only one copy of S2. Like there's not more than one S2, right? So I think this is what you maybe did, which is no, I think so yeah, you can't repeat the sinks. So you only have like one sink, and so you have to like sort of open using them. The main idea is that okay, any sink which is really bad, if it's a sink which takes 100 hours to empty something, you don't want to use that, right? Because it's just not very good. So you want to pick the first n sinks, S2 till Sn, and see what happens. So let's think of it as the amount of sink they can empty in 1 hour. S2 can do half of the sink, right? In 1 hour, S2 can do half of the sink. S3 can do 1/3, all the way till Sn can do 1 by n, right? Or yeah, something like this. Yeah, everybody good with this? Just like thumbs up if you're good, thumbs down if you're not good, right? Okay, so you have this. Now you want all of this total, when you add all of this up, is the amount of sink you can empty in 1 hour, which should clearly be more than 1 if you want to get it done in under 40 minutes, right? So it should be 1 over 1 hour divided by 40 minutes in some ways. Like you want it to be bigger than this, which is 3 by 2. So you want 1 by 2 plus 1 by 3 plus till 1 by n to be bigger than 3 by 2. And you want n to be as small as possible. You don't want to just use all 100 of them, right? Yeah? How do we do this? Yeah. So okay, in this case you can do by hand. So there's no good formula for general harmonic numbers, but maybe we'll talk a little bit about that, right? Because that's a good direction to go from here. But before we do that, let's just like, you can do this by hand. This one is not that difficult. You can do by hand. So you want to find smallest n such that words. That's wasteful. So you have first optimized and shown that you have to pick the first n. So part of the proof was to optimize and show only first n are worth picking. And so I want to emphasize on this. This is very easy to see here, but I want to emphasize on this because this is a very tricky step. Like if you don't do this step, your proof is not correct, right? If you don't do this, your argument is just that, oh, I have a way of 6 sinks which work, but maybe somebody has a way with 5 sinks.
What if you want like some of these which are greater than 2?
So, oh yeah, then you'll have to think a bit more, right? So then if you instead of 1.5 you wanted 2, then you'll have to go a bit further ahead, right? So it's not very clear how you find this in general, but I can give you some approximation. How many people are comfortable with log n, for example, log x, or have people seen log by any chance? Okay, so we won't go too much into log, but I'll give you something which is close to log, right? So I wouldn't give exactly into logarithms, but something close enough. And this is related to this particular expression. So if I do 1 by 2 plus 1 by 3 plus 1 over 2 power k, this is approximately, and I'm not saying this is a very good approximation, approximately k plus some constant. Yeah, this is roughly the case. And I won't even prove the exact k, but it's around k. It's like it could be 2k, it could be half k, but it's not like k square, right? So it could be like 2k, 4k, 10k. It could be 1 by 10k. So it's some constant multiplied by k plus some constant, like some ak plus b type of thing. Approximately this, like it's very close to this. And so how do you prove something like this? In general, you can replace 2 power k by n, and this will become log n, but you don't need to think too much about that. So here's one idea that you can use. If I have 1 by 2 power k minus 1 plus 1 plus 1 by 2 power k, so I'm splitting this in powers of 2, right? For example, if I had 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8, then I'm looking at, let's say, these 4. All of these 4 are bigger than 1 by 8, and there's 4 of them, so this whole thing is bigger than half, right? And so if you look at this whole thing, all of these are bigger than 1 by 2 power k, and there is 2 power k minus 1 of them. 2 power k minus 1 of them into 1 by 2 power k, it's half. So when I split it into powers of 2, I'm getting at least a half out of that whole thing, right? And of course it's less than 1. If you add powers of 2 reciprocals, you get something less than 1, right? Because well, okay, I'll show this in a second. So in case, I don't know if people have seen geometric progression by any chance, but if you have, then this is there. But otherwise we can give a quick explanation there as well. That's not too difficult. So keep this as a question mark for now, but this one we have proven. Right? This one is just okay. So now when I keep adding this way, I get half from here, half from the other one. So from going to k minus 1, I add a half. From k minus 1 to k minus 2, I'll add another half. And I'll keep adding these halves, right? So 1 by 2 plus 1 by 3 is bigger than half. 1 by 4, 1 by 2 is equal to half. 1 by 3 plus 1 by 4 is bigger than half, and so on. So I'll keep doing this half. So this thing is at least bigger than k. So let's see. So this we've shown is bigger than something around k by 2. You can make it if you really want. You can make it k by 2 minus 100 if you really want to be comfortable. Just so that whatever the plus 1 minus 1, you just forget that, right? And less than something like k plus 100. So for small k, this is not very good. If k is 5, 6, 7, this is obviously a bad approximation. But when k is very large, this is a pretty decent estimation. And the way you get this k plus 100 here is as follows. So we're trying to show that 1 by 2 power k minus 1 plus 1 is 1 by 2 power k. Yeah. Okay. This is less than. So this is the smallest possible denominator, right? Which means this is the largest fraction among them. So it's 1 by 2 power k minus 1 plus 1. And how many are there? There's 2 power k minus 1 there. Yeah. Everybody good with this? So this is the largest fraction, and there's at most 2 power k minus 1 of them. So when you multiply, you'll get something which is this divided by this plus 1, which is less than 1. That's where we get the one being bigger than this. So when you have 1 is bigger than this, and half is less, and you add it for all the k's, you stack it up, add it up, you'll get k by 2 on this side, and you'll get k on this side, right? And that's what we end up getting. So this is a decent approximation. The actual thing is very close. So when you have 1 by 2 till 1 by n, you get something which is approximately log n plus some constant which is called the Euler. I forget the name of the guy, so this could be wrong spelling. Constant. So this is similar to pi, e, and so on. Like this is a useful constant to have, but you end up getting this. I don't remember the value of this, but this is a useful constant which comes up at the end. So you don't have to be this imprecise. You can be very precise with the constant as well. But all of that requires much more machine. This is like an easy thing you can do without any calculus, without any knowledge of how to do that. This is just like bare bones by hand, sort of just as like if you had to guess the value, this is how you'd sort of guess the value, right? So that was sort of where you can go with this. So if you want, you can look into harmonic numbers. You can look into this type of thing from this question. And this is just like, okay, you want to make people do the question by hand till n equals 7. Afterwards, you can look up more theory, right? So that's, yeah. Everybody good with this? Everybody comfortable with this part? Yeah.
Could you just show how we would do it with integration?
Yes. So if you have something like 1 by 2 plus 1 by n,
It would be integration from t to 2 of 1 by x dx.
yeah. So you can have, let's say, something like this. It's very close to the integral. Yeah, in fact, it's this plus some o of 1 by x, 1 by n type of thing. Like it's not that big afterwards plus some constant thing. It's not that big. So, and this integration is going to give you log x. So you get like log n minus log 2, like something from there. Plus, like you do get some like extra constant type of thing here. That's sort of what you work out over there, right? So it's roughly correct. Like this is not perfect, but this is roughly accurate. Right, so and generally this is how you approximate series. So whenever you have like a series and there's like some bounded conditions, you use integration to approximate that if there's a function which you're looking at. So there is a way of doing it. It's not, again, this is not very precise, like you can make it better and so on, but and it's not clear why this is true, but once you understand integration as Riemann sums, this is not that difficult, so you can get there. Yeah. Okay. Okay. Now we move on to maybe more of a logic question. So going back from the heavy calculation, the more just straight up logic, and we discussed this a bit just in the previous session as well, so this is going to be a bit of repeat for people who are hearing again. So let's say you had knights and knaves, So these are truth tellers and liars. Okay, and everyone says all of you are knaves, right? So then how many knights are there? I mean, you've been there, so yeah. One? Yeah. So let's see how it's one, right? So okay. It's very easy to just check if there was only one truth teller and everybody else was a liar, then that's a consistent case, right? That's possible. Because why? Because when this person says all of you are liars, that's a true statement. When this one says all of you are liars, it's a false statement because one of them is a truth teller. So all of their statements are false, all of his statements are true. So then it's like, okay, his statement is true, all these are false, that's exactly what we wanted, right? So this is consistent. One truth teller is a consistent option. It may not be the only option, there may be other possibilities. So you also have to rule out other possibilities, right? So one way of ruling out other possibilities, yeah? If there were 0 truth tellers, can there be 0 truth tellers? Okay, why can there not be 0 truth tellers? So all liars are saying every one of you is a liar, and that's a true statement. Every one of them is a liar, so they can't be making true statements, right? So that's a contradiction. So you end up in what is called a contradiction. If you're in 9th grade or so on, you might have seen proofs like square root 2 is irrational, and this is done by proof by contradiction generally in class, although you can probably do it more directly as well with sort of dissent. But the point is that this type of knights and knaves puzzle is sort of a prelude you should have before you do proofs by contradiction. It will probably really help you clarify how those proofs work out. And okay, so 0 is impossible, right? If 0 is there, then you get inconsistency. What about 2? Yeah, then the knight would be lying. So
Can't say that everyone else is.
yeah, you can't say all of them are liars because this one is a truth teller, right? So his statement becomes false when it should have been true, right? So this becomes a contradiction here. So 2 is impossible, but if you write it and leave it just here, this is still not complete, right? Because you have to show everything 2 and above is impossible. So you still have one more line of logic to say, which is, oh, greater equals 2 is impossible because you pick any 2 of them and then one of the statements becomes false. So if you don't have this greater equals 2, you actually have not completely solved the problem, even though it's just like one line obvious thing. But if you don't say that, then you're not dealt with the case there's 3 truth tellers, 4, 5, so on. So you want to deal with all of them. So greater equals 2 is also impossible. And we have checked that 1 is possible. So we have checked that 1 is possible, and so we were back in this position. Everybody good with this? Yes. So the point of these knights and knaves questions is to sort of clarify basic logic, basic proof by contradiction, how you do proofs. Just like have the basic intuition for that setup, right? Okay. There's one more question here, so let's do question 11. And this is sort of like a linear equations type of question, right? Like I guess I don't know, seen this. So there's monolingual people, there's bilingual people, there's trilingual people. So maybe there's like 3 languages or something, right? So there's Sanskrit, English, Tamil. So there's a set problem, there's a set over here, and that's kind of how it was chosen. Now, monolinguals are people who are on this, let's say, shaded area. Maybe I'll use different colors, but I don't want to get into colors. So, bilingual are people who are in the cross area, and then trilingual are people who are in the circle area, right? That's roughly what's going on. So the point of the question was that you could be confused and try to do like set Venn diagram stuff, like try to use these different counting things, but you don't have to. You can just say M be the monolinguals, B be bilingual, T be trilingual. You're given these equations. 21, M plus B plus T is 1000, M plus 2B plus 3T. Yes, so 3 variables, 3 equations. But usually I think in 10th class you only see like 2 variables, 2 equations, right? So 3 might be a little uncomfortable. But point is that this is not 3 equations, this is just 1 equation. Because you can just have like B can be written in T plus T in the form of T. M can be written in the form of T as well, right? With M you can write M as 1000 minus 21 minus 2T. And then you can have the last one where everything is in a linear equation in 1 variable. So you have 1000 minus 21 minus 2T plus 2T plus 42 plus what is this last one, plus 3T is 2, 2, you get something like this, right? So maybe 2t and 2t goes away, you have 3t, yeah, so you have 3t plus 1021 is 2200, 3t is just like minus 21 plus 42, right? So that's like plus 21, then you get t is 400 minus 7, 393. So you get t is 393, then you can check the rest. I think you end up getting m is 193, right? You can end up getting something like that. Right, so everybody comfortable with this? The main point of this question, and which I really want to point out, is that if you have only seen linear equations in 2 variables at most, like you have seen m and b, you have seen x and y, and now you're suddenly seeing linear equation 3 variables, that's not a cause of concern. The exact same method works for all of them, is that you pick any one variable, write it using the remaining ones, make it a smaller number of variables, and then just like solve the whole thing out. So for linear equations, everything you need to solve linear equations is just sort of one variable linear equation solving, like be able to solve ax plus b equals c, and then from there you need to be able to just write everything in one variable. So convert everything in one variable, solve that equation, right? So the approach you have for 3 variables is the same as for 2 variables, and it's effectively the same as for 1 variable. And this leads to a more general algorithm for solving linear equations. There's a proper algorithm, which is, I mean, you might call it like substitution method, but there's something, yeah, something with matrices called row reduced echelon form. So you can use that to solve linear equations in general. But you don't need to worry about that. For now, most linear equations that you'll see, you can just do by hand. It's like do all this, do by hand, and it'll be good. Right. Okay. Any questions? Everybody thumbs up with it? Okay. And now we move on to maybe more questions. So there's question number, let's do 12, 13, and then we can go back to that sort of homework from yesterday, right? So that sounds like a reasonable plan for today, because 14 and 15 I want to spend more time on with like more modular arithmetic before we get there. 12 and 13 I think we can do with just logic alone. So 12, we have A1, A2, A250, A251. We have, or in this case I think it was 1000, right? Because I don't know why it's 1000 in one and 250 in the other. So A1000, A1001. Just like different numbers for some reason. I don't know. So A1 says A2 is a liar. A2 says A3 is a liar. A1001 is a liar. Says more liars, and more I mean strictly more, so they can't be equal. More L's than T's in 1 to 250 or 1 to 1000. 1 to 1000, yeah. So these are all the statements that they make. How many liars are there among them, right? How many knaves are there among them? So what do you guys do for this one? You've seen it too. Yeah? They should alternate, right? That's the correct.
So this will be 500 times 500
So
Yeah?
8001 is lying.
8001 is lying, yes. So all these are correct answers. So I'm happy that there's correct answers. I also want to get to the correct method, like how you should think about this. I think it's important because it's easy to overlook some detail here. So I'll show you what the detail would look like. So let's say I start with A1 is a truth teller. So if I assume if A1 is telling the truth, so A1 says A2 is a liar, this implies A2 is a liar, right? And if A2 is saying, if A2 is a liar, and A2 is saying A3 is a liar, that's a false statement, so A3 is a truth teller. And if A3 is a truth teller, then A4 is a liar, because A3 is saying A4 is a liar. And you keep doing this chain, right? Keep doing all of this till you reach A1000 is a liar, and A1000 says A1001 is a truth teller. But what is A1001 saying? It's saying among A1 to A1000, more L's than T's. Right? So in this case, what you're saying is this, but in this case, there's actually 500 T's, 500 L, right? Because it's odd and even. So A1001 statements which should have been true is false, which implies A1001 is false. So you have something which is true and something which is false at the same time. That's a contradiction, right? It's a contradiction. So this is impossible. A1 cannot be a truth teller. Yeah? So this implies A1 is a liar. Now you still have work to do, because it can happen that A1 is a liar is also a contradiction, and then the problem does not make any sense, right? So you want to make sure that this is consistent. So if A1 is a liar, that implies A2 is a truth teller, as we did before. Implies A3 is a liar, plus A1001 or A1000 is a truth teller, which implies A1001 is a liar. So now we need to check whether A1001 statement actually is a lie. And it is a lie, because from 1 to 1000, 500 T's, 500 L's. So A1 1001 is indeed a liar. So this case does not give you a contradiction. Earlier case gave you a contradiction. So in some sense you can make a mistake and think the earlier case is correct and still get the same answer, but it's important to have that distinction in mind, that you need to rule out one possibility entirely. Sometimes both cases are consistent, in which case if you get the same answer, that's fine. If you don't get the same answer, you can't determine the answer, right? And sometimes both cases are inconsistent and the question doesn't make sense. So if there are options, there will be many options you need to be aware of, right? In this case, this one is a liar, and then there's alternating ones. So 1 plus 500, so 501 liars in total, right? And of course, knowing this sort of contradiction thing is really important. It's really important to have that contradiction embedded in your mind. Yeah? Everybody good with this? Any questions about this? Sounds good. I don't know where this is. Okay, so then we can do question 13 before we move back to yesterday's square root thing. So question 13 is my favorite in the test. I think it's probably the most interesting question because it's very fun. So let's see. So you have 3 people. Let's Bob Carroll, let's say. 15. So this is how many games they play. They play table tennis. They're playing this game. And they use the following form. So in table tennis, there's no draws. So it's only going to be winners and losers, right? So if 2 people are playing, and one person wins, the other person loses, then the person who loses moves aside, and then the third person joins in to play the winner. And then they keep doing this. Whoever wins, we don't know the outcomes of these matches, right? So they keep playing in this fashion. How many games did C win? Just from this information alone. Yeah?
So the answer is 0.
Yeah.
So basically, we let the games played between A and B be X,
Mm-hmm.
and let the games played between A and C be Y.
Mm-hmm.
Now we know that A has played 17 games. This means that X plus Y is 17.
Yeah.
And also B has, so basically the games played by B would clearly be 17 minus X.
Mm-hmm.
And similarly,
Yeah. Okay. So maybe let's do it this way. So let's say A and B. This is, I'll use the X, Y, Z type. So I'll call this Z. B and C I'll call X. C and A I'll call Y, because X should be A, Y should be B, Z should be C. So use that, right? So this is the number of games they played with each other. So with A, it is AB plus AC, which is Y plus Z. B, this is Z plus X. C, it is X plus Y, right? So these are your equations. That's what you're saying, right?
yeah.
Okay. Can you solve X, Y, Z using this? Can you figure out X, Y, Z using this? Yeah.
So just sum all of them and divide it.
Yeah, exactly. So when you add all of them up, you get 17 plus 15 plus 10 is equal to 2 times X plus Y plus Z, right? And this thing is 42. So you end up getting X plus Y plus Z is 21. So total 21 games were played, right? You can also see it another way without doing the XYZ algebra. You can just say that if you add all of these games, every game is counted from both players' sides. So it's twice the number of games. So twice the number of games is the sum 17, 15, 10. You can count it that way as well. And in that case, it doesn't matter how many players there are, so you don't have to do all of these equations. So it's a slightly faster way. But you end up getting this, X plus Y plus Z, so 21 games in total. Yeah? Okay, what's next? What's the follow-up then?
So basically, we make 2 cases.
Mm-hmm.
If we played the first game, if C played the first game or not. Or
Okay.
no.
Okay.
So if C played the first game,
Okay.
this means that C would play a minimum of 11 games.
Yes.
So that can't be possible. This means that C would play the second game, and if C plays the second game, there's a minimum of 10 games.
Yes.
So hence C will lose all of them.
Yes, that's the idea, right? So it's like, okay, no matter how one game ends, let's say X and Y played this game. I won't use ABC. Let's say X and Y played this game, and let's say x1, and now z will play. So x and z will play. Okay, whoever wins or loses between x and z will play y at the end of this round, right? So nobody can skip 2 games in a row. So no one can skip 2 games in a row. So that's one observation. Second observation is that if someone skips a game, they lost their previous match. Previous game, right? Because if someone was winning, then they will keep playing, right? So no one can skip 2 games in a row because they have to cycle out afterwards, after the second game. And then if someone skips a game, then they lost their previous game. These two are the observations, right? So if C started with 1, C played in the first game, then must play at least once more from 1 to 3, at least two times more from 1 to 5, and so on. So they must play at least 11 games, right? So whoever started at 1 must play at least 11 games because they can only skip at most 1 every time, right? Everybody good with this logic? So C cannot have started at 1, so C must have started at 2. This is the first game C played, and then C must alternate every time, right? Because C cannot play consecutive games in a row, otherwise okay. So from 2 you have, let's say 2, and let's say either you play 3 or 4, or you play from 3 or 4, you keep branching, right? So keep drawing these possible arrows. If you only have 10 games and you still have to reach at the end, you don't want to miss any 2. So between any 2 games of C, there's a gap of at most 2, right? So okay, maybe let's say C has 10 games. Starting at 2, there's a gap of at most 2. So you have 9 more games and a gap of at most 2 plus 2 into 9, 2, so that's 20. So max that C can reach with this is the game 20. And if C wins anything in the middle, max it will reach is 19. So then then you have 20 and 21 which C does not play, which can't happen. So C must lose all games. So C only plays the games 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and C must lose all of them. That's the only possible thing which can happen with C. So you can completely predict the order of all of those games and how C goes. I imagine if you think very hard, you can also reduce the possibilities for which games A1 and which games B1. You can also make some progress there. But this is the easiest thing to do. Like C, you can figure out the entire chart, and that's kind of what happens, right? So this is one of those examples where the algebra, if you just try to solve it using equations, you won't find enough equations to solve the question. But you can use inequalities, and this is like a sharp inequality. This is the only case where the inequalities can be satisfied, right? Because for example, if C won the second game and played the third game, now whatever C does will at most reach 19, and then 20 and 21 he'll have to set out, and he can't set out 20 and 21, right? So if at any point these two become consecutive, there's not a gap of 2 at any point, then C will at most reach 19 and never reach 20 and 21. That's kind of the logic here, right? Everybody gets the proof? So this is one of the fun questions because you don't have enough information. It doesn't feel like you have enough information to say who wins or who loses any game, but then turns out you have enough information to say the outcome of 10 matches. Like you know who the player was, you know who lost, right? So that's sometimes what happens. Everybody good with this? Everybody comfortable here? Okay, then let's do. Okay, now we can maybe go back to yesterday's homework thing. So we're trying to do. The square root of this thing was 34, right? And square root of was 334, that was the answer. And then we claimed it was 3334. The claim was that this continues, right? Everybody good with this? Okay. And also if you want square root of 16 is 4, so when you have 0 3s and 0 1 and 5s, so then in that case that's also, so the pattern starts from very beginning and then keeps extending, right? So can you make the general claim? This is 2n digits equal to n digits for all n. So can you prove this? So any ideas people had for this? Any ideas you had? So you can use induction, that's possible. It's a lot of calculation. GP also you can use, it's a lot of calculation. Try to do it without induction and GP. Try to do it some sort of like street fight way as well. Like try not to use both, because I imagine for GP and induction both are like 11th grade topics, right? So even the sort of like later end of part 2 would not necessarily be familiar. I mean, if you read it, that's good. But you can use both approaches. You can use induction, you can use geometric series, and you can figure it out. But try doing something which is very street fighty, which does not require any of this. It's just basic algebra, right? Like just algebra. And I would recommend focusing on this number because it's easier to focus on. Try to focus on this number. See how you can rewrite this number. So see what you can do with this number. This n times 3 and 4. Where does that come up? Okay, if there was no 4, what would you think? If it was just a bunch of 3s, what would you think? Yeah? It's? Oh no, I mean if you, okay. What I mean is, let's say you just had this number and no other question. There's no question, there's just the number. What's your first instinct to do with this number?
Take out 3.
You can either take out 3 and you have 1, 1, 1, or you can do something else, right? Or you can multiply and divide by 3 and you have 1 by 3 and then 9, right? So if instead of 3 you have 4 at the end,
You can do take out the 4 and write it as 3 plus 2.
so you can just do this, but now you have 1, 0, 0, 0, 0 and 2. So for example, 4 is 1/3 of 12, 34 is 1/3 of 102, 334 is 1/3 of 1002, and so on, right? It's a little surprising, but you can make this work, right? So you just get enough zeros in the middle. And how many zeros do you get precisely? You get like as many zeros as 3's, right? So there's n zeros here that you end up getting. Everybody good with this? So if I move to the next page, so effectively I can say this is equal to 1 by 3, 1, 0, 0, 0, 2, and then you can write this in an exponent way, right? You can write this as 10 power, so this is 10 power 1 and all the way till 10 power n and 10 power n plus 1, right? So 10 power n plus 1, this is what your number is. So you don't need any GP formula, you just like need to add this, right? It's just carryovers directly. So when you square this, when you square the whole thing, you're getting 1 by 9, 10 power 2n plus 2, 4 into 10 power n plus 1 plus 4. Yeah? Looks good? How do you simplify this? It's still not that good, right? Still not great. How do you simplify this then? How do you sort of make your way around this? So maybe try using the 9. We can use the 9 maybe. Yeah? Yes, exactly. So now you have 10 raised to the power 2n plus 2 minus 1, 9. 4 into 10 raised to n plus 1 minus 1 by 9. So I'm doing a minus 1 here, a minus 4 here, which becomes a plus 1 in total. Right? So it's a 1 plus 4 plus 4. So I can rewrite it this way. Looks good? Everybody good with what this looks like? So this is equal to 1, 1, 1, 1, 2n plus 2 times, plus, going back, 4, 4, 4, 4, 4, n plus 1 times, plus 1. And this you can add, right? So the first n plus 1 digits become 5, because you have 1 and 4, there's no carryover. 1, n plus 1 times, 5, n plus 1 times, plus 1. And then this becomes 1, n times, 5, n times, and this 5 and 1 gives you 6 at the end. Because you have 5 and 1 gives you 6. So one of the 5 shrinks away, and then I just group it here like this. I keep this one outside. That's the form we had, right? Everybody Good with how this turned out? Oh yeah, and there's n here and then 1, so yeah, you can write this whole thing as n plus 1 times. Yeah, I'm just doing it to match the numbers, just to do this. Yeah, because the number of 1/5s in the middle, nested ones, is the same as the number of 3s. Everybody good with this? So you don't need a GP formula, you don't need induction, you can just do like direct sort of calculation, and there's no carryovers anywhere, so you can make it work, right? There's more interesting questions on this, but they become increasingly very difficult, so I don't want to get into that. But there is a question about, let's say, if you have a sequence of squares which looks like this, then can you deduce that it must be of the 3 through 3 form? That's a more difficult question, but this has more depth. This is not the end of the story. There's more to the story afterwards as well. As an exercise, maybe you can try seeing. So I don't know if this has a pattern, but I suspect it has a pattern. So if you want, I can maybe write a code to check whether there's a pattern or not. You know, it's like, okay, we can quickly check if there's a pattern or not. But my suspicion is if you do this should also be quite good. I imagine this should also have a good form. Maybe we can try calculating. Okay, so what's 7 square? It's 49. 67 square, what's this one? 3600 plus 49 plus what's the last one? Someone will have to help me out with this because 840, right? Yeah, that's correct. It's 4489, I think. Yeah, I think this will continue. Like the 4489 thing builds up. Like the 48 will build up in the middle, I think. I imagine this will just be like, let's quickly check 667 square instead of writing the full code. If that is correct, then we are good, right? So 667 square. Yeah, so that, yeah, so 667 square is equal to 444889. And then this just builds up, right? So you can check, you can use your calculator to check this next few terms. Oh, sorry, this is this one. 48889. This keeps building. And then you can use the same type of logic. So you can maybe use this as an exercise for checking if you understood the previous one. This one you'll have to be a bit careful. You can't just multiply by 3 in some sense. You have to do something, or even if you do, it will become something more. So if you multiply by 3, it will become something slightly different. Yeah. Yeah, it's a little surprising, but it's nothing too bad. Nothing too bad here. Everybody good with this? Okay. Yeah, and this type of thing is generally, I think it catches your eye when you first see it. And we still have time, so maybe we can do a bit of discussion on modular arithmetic. So how many people have seen modular arithmetic by any chance? Like, I've seen some of it. Okay, I'll still give a very brief introduction just to get people on board on the same page, and then we can see how to do calculations with it, right? So some of it will be simple, and tomorrow we'll have more complicated things with it. So imagine you have a clock. So you have a clock, right? And this has 12 parts. So you have 1, 2, 12 things, right? So if I tell you what will be the time 13 hours from now, you'll be able to tell me the time, because 13 minus 1 is 13 minus 12 is 1, so it's like 1 hour ahead of what's right now, right? So if right now it's like it's about to be 12 right now, in 13 hours it will be 1. In 71 hours, what will be the time? So you can just do 11, right? Because 71 is 60 plus 11. So 60 is like 5 rounds of 12 plus 11, right? 72 minus 1 also. Yeah. So you can just, whatever the integer amount I tell you, you'll be able to tell me the time using the clock, right? Is that if I tell you after A hours, what's the time? So what you'll do is you'll subtract the closest multiple of 12 you can find. So 12 times, I'll write something which if you're not familiar, you don't need to worry about it immediately. 12 times this is called the greatest integer function of a divided by 12. So you divide a by 12. So let's say I divide 71 by 12. And I look at the integer which is smaller, the largest integer which is smaller than this. So 5 is smaller than this, but 6 is bigger than this. So I just look at 5. So 12 times a divided by 12, and you look at the greatest integer. This is going to be your answer, right? This is going to be the increment from your current time. You add this much time after this many hours. So in some sense, you're going in cycles of 12. You can even ask what was the time 12 hours ago, or you can even ask what's the time 71 hours ago. And then it just becomes like minus 71. And there you're saying, oh, it's minus 72 plus 1. So it must be 1.
You can also say 8 is complement to 6 modulo 12.
Yeah, yeah. So exactly. So point is you can just do, so you can relate these times. So which times are the same? the times which are differing by multiples of 12. So time A is same as time B if 12 divides A minus B. And can be positive difference, negative difference, we don't care, right? The two times are the same if they differ by a multiple of 12. Right? So then we say A is congruent to B modulo 12. Like this is the notation for 12 divides A minus B. Okay. Everybody good with this? And the funny thing is, you can have strange clocks which don't have 12. 12 is just a random number we chose, right? It could be any number. So you can have a clock which has 31 spokes, for example. It can just be a wheel with 31 equally distant arms. You can still have a clock like that, right? You can have a very strange clock, and you still have the same type of thing happening if you define your hours differently.
For general, you can write A is equal to B plus C and where N is an integer.
Yeah. So you can have your clock which is C spokes, for example, like C can be any number, and then you say A is congruent to B mod C if A and B will give you the same time, which is same as, so this is if and only if symbol, C divides A minus B. And of course, by definition, every number divides 0, because 0 is just 0 times the other number, right? So for example, 121 divides 0, because 0 is simply 0 times 121. So here, if A minus B is 0, that's obviously they're pointing at the same time. Otherwise, it's like, okay, you cycle around, you just look at whether the difference is a multiple of C. Now there's some cool properties which emerge from this. So if A is congruent to B mod C, so I'll use maybe some algebra, and A2 is congruent to B2 mod C,
Then A1 plus A2 is congruent to
B1 plus B2. So you can just add all of them together, right? And why is this true? Well, intuitively it's true because it's like if after A1 you have the same time as after B1, and if after A2 you have the same time as after B2, after A1 and A2 you should have the same time as after B1 and B2, right? So you're kind of just doing the same operation. It makes sense, right? The proof would be just like, okay, C divides A1 minus B1 plus A2 minus B2 because it divides each of them individually, and then it divides the difference, right? So this is the difference here. You subtract it here, get this.
And also A1 is congruent to B1 mod C, then A1 minus B1 is
Mhm.
congruent to 0 mod C.
Yes, yes.
You can subtract,
Multiply,
or
yeah.
add on both sides. But
Exactly.
You can't divide.
Yeah, divide you have to be careful. So you can in some cases, but not always. Like divide, you have to be very careful when you can divide. So there's a reason we will get to why. So okay, maybe we will not talk about when you can divide because that's slightly more subtle. You need to be more comfortable with GCD, for example. But yeah. So if you do A1 A2 versus B1 B2, that's also going to give you the same. That's a slightly surprising one because it's not very obvious what multiplication here would look like, but it's still not that difficult. And the proof is slightly interesting. So I'll do the calculation for the proof. It's a very common calculation. It comes up in contexts outside this. So this is the same calculation you do when you're proving product rule, for example, when you're doing differentiation. So it's the same type of thing. So A1 A2 minus B1 B2. I'll write this as A1 A2 minus A2 B1 plus A2 B1. So I'll minus A2 B1 plus A2 B1. So I'm adding the 0 to this in the middle. And now this becomes A2 times A1 minus B1 plus B1 times A2 minus B2. Right? Now this is a multiple of C and this is a multiple of C. They're both multiples of C and you are multiplying them by some other numbers, adding them, still a multiple of C. So C divides this. Right? So this is the basic sort of property of remainders. And now with remainders you can find a bunch of stuff. You can now find something like what's the remainder? So this can be a good exercise to sort of get your ideas flowing. This could be a good exercise.
Triple 1 to the power triple 1.
Oh no, sorry, not square root, sorry, this is long division. Or this is just long division. So you just find the remainder when, okay, I'll maybe write it this way. So maybe you can find this mod 13. So find the remainder when this is divided by 13. Right, so this can be a sort of good exercise to get you comfortable with all these operations. And like try to work this out. You still have some time, so we can, I think this is the example we can work out. And tomorrow we'll work out the rest of the questions and more modular arithmetic just to get used to this. Because we've finished the logic part. So this test was about logic, a bit of maths and a bit of sort of this number sense, like this intuition about numbers and how they leave remainders, how they estimate things. So how big something is, how small something is. That's the kind of basic intuition we want. So how do you plan to do this? What would you plan to solve this, right? Oh yeah, so no theorem, only the stuff you've seen so far, right? No theorems. So just what you've seen so far. So okay, it's congruent to minus 10. 104 is a multiple of 13, right? It's 13 into 8. So this is like 7, I think. So 111 into by itself. Yeah. So this is 7, and then even if you do one more, it's still by 7, right? It's the same property we are using. So you forget the 111, make it 7 first, right? So this is congruent to 7 power 111.
And you can also replace the top ka 111 by 7.
That you cannot do. That you have to be careful. You can't replace the top ka 111 by 7. So you have to be careful. I'll show you why. If you do, then okay, then you'll run into something. You can try that, and then you can compare the answer. Right? You'll run into a problem there. That you have to be careful. Yeah.
You could do it another way. If you write it like 13 times 8 plus 7. Right. So basically that's just 13 times 8 plus 7 times 13 times 8 plus 7.
Yeah.
111 times.
Yeah.
So obviously like
Only the 7 stuff comes out. Yeah. Everything else. Yeah. Exactly. So what he's saying is also a good trick. It's a useful thing for when you're doing, let's say, binomial algebra of some sort. If you're thinking of this as this product, right? In this, each of these terms you're picking one randomly. You're picking one here, and so on. Either you're picking 13 times 8 or you're picking 7, right? Anytime you pick 13 times 8 already becomes a multiple of 13, so you don't care about that. So the only thing which gives you the remainder is the 7. So you pick 7 1 times. That's also a way of seeing why you get 7 power 1, right? And now you have to find this modulo 13. So how do you find this modulo 13?
Maybe we can do like repeated times until we get to number like 1 or minus 1.
Sure, that's a good idea, right? So 7 gives you 7 remainder when you do 13. So this is mod, which means modulo, which means sort of like just cycling out. 7 square gives you 7 into 7, 49. And then you subtract like from 52, so that's 10, right? 10. Then 7 cube gives you 7 into 10, which is 70. Subtract 65 gives you 5, right? 7 power 4 gives you 5 into 7, 35, which is 9, right? 7 power 5 gives you 7 into 9, 63. That's 11. 7 power 6 will give you 7 into 11, which is 77, which is 12, right? Now you can do something smart. So 12 is same as minus 1. 7 power 6 gives you minus 1. So if you square it, 7 power 12 will give you 1.
Could also do this using Fermat's theorem.
Yeah, so we can do Fermat's theorem, but we've not introduced Fermat's theorem, right? So we are trying to do it with machinery we have introduced. So you get 7 power 12 as 1. Now if you take this to a very large power, so you get 7 power 96, that'll still be 1, right? Because you're scaling up to 12. So you have 7 power 96 is 1 mod 13. I'll drop the mod as well. I'll just do like this and 13, right? Drop the mod as well. So 7 power, and you can even go further, 7 power 108 maybe. More 12 is still 1, right? So 7 power 111, 7 cube. Because you just have like plus 3, right? 7 cube we already found was 7 cube was 5, yeah. 5 or 13. So the answer will be 5. Right? So you can make it work this way. There's a theorem which tells you that 7 power 12 should have been 1, not 13 in the first place. There's a theorem which tells you that, which is the Fermat's little theorem. So I'll not prove this, but okay, maybe if we find time we'll talk about it. Okay. Okay, no, I want to write this in the other form because otherwise I have to specify coprime. We don't want to use the word coprime. P congruent to A mod P. So if p is any prime number, then a power p is same as a mod p. That's for Russell theorem. So 7 power 13 is same as 7. Yeah? And then 7 power 12 is 1 from that. But this is true even if you had a was 13 itself. That's still true because they're both 0. But here you can't say that 13 power 12 is 1 mod 13. So there you have to specify that.
Condition was that A and P should have GCD as 1, right?
Oh, that is if you have p minus 1. So this is true for all a. That is true if a and p, if p does not divide a. It's a different condition. Yeah, it depends on if you want the p minus 1 version or the p version. I stated the p version because I didn't want to state this sort of condition, but you can state it conditionally as well over here. Because if a was p, then this will be false, right? This will not be true, but otherwise it's there. Yeah, so we'll start from here. This is a good exercise to get started, and then we can build more. So I'll give one question to everyone just so they can think about as a small homework type question, maybe just before tomorrow's session. Let's see. Okay, you can try doing one of two things. So prove that. That's first thing. And second is that if you look at the number 2 power 29, this is all the digits from 0 to 9 except one of them. So except one of them, it has all the digits, right? So there's some missing digit except maybe let's say 7 is missing, then it has all the other digits except 7 when you write it out. Find the missing digit. Bonus points if you find this without actually finding the number. If you find the number, then you can just look at the number, but without, okay, find the missing digit without finding the number. The number. So you should not know what the full number is, but you should know the missing digit. So can you find it using this information? So these two could be fun homework problems you can sort of think about, and I think if anybody is staying for part 3, we'll solve them, so you won't have much time to think about them, but we'll do these and some more modular arithmetic for part 3 today, and then yeah. So you can take a break and then put a banner for now, and we'll begin for part 3 later. Yeah. So any questions? If you have any questions about today, you can ask me. we'll start the stream. Yeah, okay. So welcome back everyone. We'll do day 2 for this session with part 3 today. And following up from yesterday, we'll do some modular arithmetic first, some remainder stuff first, and then we'll solve more questions from our assignment, and then maybe we can proceed from there. So how many of you are familiar with modular arithmetic? Like how many of you have seen modular arithmetic? So this would be stuff which looks like, it looks like this. So have you seen this type of thing before? Okay, not everyone. So we'll go from the very basics. We'll start from the very beginning and very quickly build up. So this will build up, like everything you need to know will kind of just build up very quickly, right? Okay, so you've seen a clock, right? Like 12, 1, 7, the general clock. Currently it's 12, right? Or 12 plus something, we don't know. But if it's 12 and I tell you what will be a time after 71 hours, so then you can just find that time, right? It will be 11. The clock will be pointing at 11 at that point. And if I ask you what's the time 109 hours from now, it's going to be 1, right? So how do you know what that time is? Like what tells you that, what's the process which tells you that time? Yeah, so in this case if we just care about 12, we don't care about the full 24 clock, we'll just care about 12. So let's say it was 109, it's same as, in some ways, 109 minus 108, which is 1. That's it. Being 109 hours ahead acts the same way as being 1 hour ahead. Being 109 hours behind, so if it's behind I'll do minus, is same as 11, which is minus 1. Right, so these are all same in some ways. So when we have this type of relation which sort of makes two things equal, it's an equivalence relation, right? Equivalence relation. And the way we say this is congruent. So we'll say 109 is congruent to 1 modulo 12, which means that the remainder that 109 leaves when divided by 12 is 1. Right? In general, if you have a number A is congruent to times mod 12, right? Where this is the greatest integer function. So you have A divided by 12, you take the greatest integer function. So for example, if you have 71 divided by 12, greatest integer function is 5, right? So it's like 71 minus 12 into 5 is 11. Yeah, so 71 is the same as 11 modulo 12. And in general, you want your remainders to be between the 0, 1, 11, like you want it to be here. So you don't say 12, you say 0 because it's just easier to work with 0. And so we usually want our remainders to be in this set at the end, right? But notice that there's nothing special about 12. 12 is just a number of things on the clock. You can have a strange clock which has 31 of these, which has 41 of these, and you can still do the same type of logic here. So 12 there's nothing special about 12 there. So if I have a clock with M spokes or something, I don't know what it's called, spokes, then being A hours ahead is same as being B hours ahead. So we say A is congruent to B modulo M if and only if M divides A minus B. So this is same as M divides the difference. So being 100 hours ahead and being sort of 171 hours behind is same as being within 271. So if M is a factor of 271, you'll end up saying that they're the same time, right? So yeah, so for example 100 is same as minus 171 modulo 2. I won't even use modulo, I'll just do the brackets and write it here. Okay? So these are the same because when you take the difference, 271 divides the difference. That's just how you connect these numbers. And this is a very smart way of sort of doing a new kind of number system. Instead of your numbers being, so earlier we go from integers to rational numbers, from rational numbers to real numbers to complex numbers. That's a different way of expanding your number system. This is a way of sort of shrinking it, like you're saying that, oh, you have a number line for integers and then you glue it together. So you have a line like this, 0, 1, 2 till M, and then you glue it together. You glue M and 0 together, make it a circle, right? That's kind of what this action is doing in some ways. Everybody okay with this? Okay. So from here you can say a bunch of other things. You can now do operations in algebra on this new number system. If you have a new number system, you want to do algebra on that, right? So if in my number system, if A1 is congruent to B1 mod M, A2 is congruent to B2 mod M, then what you end up getting is that A1 plus A2 is congruent to B1 plus B2 mod m, right? So why is this? Why is this true? So you can just check out definitions. So A1 plus A2 minus B1 plus B2 is A1 minus B1 plus A2 minus B2, right? And both of these are multiples of m. So if you're adding two multiples of m, it's still a multiple of m. So multiple of m, multiple of m. So you're adding both of them, still will be a multiple of m, right? So m divides this thing as well. So that proves that if two of these are the same, then their sum is also the same modulo m. So this is quite nice because it means that your equivalence is actually like, okay, it respects addition, like whatever addition does on numbers, you can expect that to happen for these remainders as well. Everybody good with this? It's like thumbs up if you're good. Yeah. Okay. What about multiplication? E2 mod m. Does that mean A1 A2 is congruent to B1 B2 mod m? So yes, no, unsure. Unsure? Okay. So let's try working out. So this is true. If this is true, then this is true. But the proof is a bit tricky. It's not the same proof, and some of you might appreciate where the proof is coming from. So I want to show m divides A1 A2 minus B1 B2, right? This is same as if I add and subtract A to B1. Yeah, same as if I do this trick. And you might have seen this trick when you are proving something about what's it? When you're taking derivatives and differentiating it. It's like quotient rule and some other stuff, and you're doing this type of derivative. This kind of trick comes up, right? Where you add something, subtract something else. So it's a very common trick in maths. It comes up everywhere in analysis. It comes up in Fourier analysis. It comes up in your differentiation. It comes up in number theory as well. It's a common trick. B1 plus B1 times A2 minus B2, right? And then you know those two exactly. So this is m, and m divides this one as well. So m divides this now. Yeah. So now it's like this is completely algebra now. It's like, okay, whatever we were doing in algebra, we can now do here as well. We can add and multiply. That's enough to go business now. Now we can do business with this. Okay. And in particular, if A is equal to B mod C, you can now take powers as well. You can say that, oh, they have the same. So A to the n is same as B to the n now. Take powers and everything is fine. So just to get you started, we can have a small, we did this I think earlier as well with the previous cohort. So can you find this modulo 13? So you can start from here. So 111, power 111. It's a huge number, right? It's an unbelievably big number. Can you find the remainder when it is divided by 13? So just using the rules we have seen so far. Yeah? Just like try to come up with the steps of it, like what would the calculation feel like? Yeah? Yeah? So this is same as 7, right? Because 101 minus 104, and this is like 13 into 8. So 7. And so this is congruent to 7 power 111, right? So let's try to do some small values for 7 just to see how it's performing. So 7 square, 49, that's 10, right? 7 cube is 70, so subtract 65, that's 5. 7 power 4 is 7 into 5, 35. And now from 39 you can subtract and get minus 4, so even it's okay to write the minus as well sometimes. Sometimes it's easier to work with the minus, right? Because 35 minus 4 is 39. So if you want, you can also make it, like you can play with the negative numbers to make it easier. 7 power 5 is 7 into minus 4, that's minus 28. And then you can add 39 to it. So now you make, or you can add just 26, make it minus 2. Right? Just add 26, make it minus 2. So 7 power 6, minus 14. Now you add 13 again, make it minus 1. Minus 1 is good, right? Because now if I square the whole thing, it's 1. Everybody comfortable so far? 7 power 12 is giving me 1. So if I do 7 power 108, that's going to still give me 1, right? Because you have 7 power 12 is 1, take the whole thing to the 9th power, still 1, right? 7 power 111 is just 7 cubed now. And 7 cube is giving me 5. So the whole thing is now 5 mod 13 will be the answer. So 5 will be the answer now. So we're very quick. It's like once we notice a few patterns, once we get to -1 or 1, suddenly everything becomes easier, right? And there's a deeper reason why you'll always end up getting -1 or 1. So eventually, if you're, or in fact you'll always get 1. If you have any prime number that you're dividing by, and you have anything else, and you keep taking powers, eventually you'll get 1 somewhere. So, okay. Sorry, yeah? This is a Fermat's little theorem. We'll prove something slightly weaker. We won't prove something as strong as Fermat's little theorem, but we'll maybe do something slightly weaker. So, but is everybody okay with the proof that 1 on 1 power 1 on 1 gives you 5, right? Everybody good with this? If I look at all of this, and I'm looking at this modulo p where p is a prime number. So I'm maybe looking at all of this modulo 7, let's say, just as an example, but you can replace 7 by any prime number, you get the same thing. Why will I get a 1 somewhere in the sequence? So the point is, okay, you don't know you'll necessarily get a 1, but you know that some two things will become equal, because the sequence is infinite, right? You have a square, a cube, you keep on writing all of this. Infinite sequence, there's only finitely many values it can take. Like all of these numbers take value from 0, 1 to p minus 1, right? So after p terms, for the p plus 1th term, some 2 will become equal. So if I look at a square, a to the p plus 1, some 2 of them must be the same one, right? You have like p plus 1 things shoved into p things. So some 2 of them will map to the same one, right? So let's say a power I is equal to a power I plus j maybe. I plus j is the bigger one. That means that p divides a power I, a power j minus 1. It's by subtracting the thing and taking a power I in common. Now p does not divide a power I. We assume p does not divide a power a initially, right? Because if p divided a, all of this would be 0 anyway. Then there's nothing to do there. So we are assuming p does not divide a initially. So p divides a to the j minus 1. And j is something small. So a to the j will become 1 eventually. Right? So now you will have a 1 in the sequence somewhere. So that's good. It's like, okay, now a to the j is 1 on p. And this is very good because it tells you that in fact j is not that big. Like you know that j is less than p. Because you can look at a to the I plus 1 and so on within p. So j is less than p. So within the first p you'll end up finding 1. It just so happened we were unlucky, and for 7 we had to reach all the way till 12. But we were guaranteed that between 1 and 12 there will be something. The 7 power that thing is 1 more 13. So we were guaranteed to have that. But it was just that we were unlucky and 12 was the only thing which was then, there's nothing before 12 which gave you this. But there's a general theorem by Fermat. Maybe we won't have time. If you have time I'll prove it, but if you don't have time we won't prove it. In fact a to the p is same as a mod p for every prime number p. For every prime p. And more precisely, if p does not divide a, so this is true even if p divides a because then both sides are 0. If p does not divide a to the p minus 1 is 1 mod p. So 12 is 13 minus 1. That's where we get this, yeah?
If a to the p is a mod p, then when we had 7 to the power 111, it would have just been 7 and we could have taken the 6 from there.
Exactly. So when we had 7 power, you're saying this? Yeah. Yeah, this just becomes this modulo 12, right? So you remove the, or you, yeah, so it's like, if you do this modulo 13,
This is only true when there's mod 1 and
no, mod 13, sorry, oh yeah, if this was mod, okay, this is not true because this is not prime, right? Not prime. So you need this to be a prime number, it's not true for like other numbers. But if you're doing this mod 13, now you know 7 power 13 is 7. So maybe you have like 7 power 26 is 7 square. So using 13 is not the best way because then what happens is you get a square cube again. But if you use 12, 7 power 12 is 1, now you can use 7 power 108 is 1. So you can go straight away. So, and this one tells you that it's p minus 1 is the right one. And it just so happened that for 7 nothing smaller works, sometimes something smaller works as well. Sometimes you can have a smaller number which works as well, usually it doesn't. In fact, if j is, so there's also more, so we won't prove any of this, but you can look it up, this is Fermat's little theorem. If we have time we might prove it tomorrow, but yeah, we'll see. I'm not guaranteeing we'll have time to prove this. But there's more interesting stuff. If a to the j minus 1, if p divides this, and j is like, let's say, less than p, and let's say j is the smallest. So for anything between 0 and j, this does not happen. J is the first time where a to the j is 1 mod p, right? then j divides p minus 1. So j is a factor of p minus 1. So the only things which could have worked were factors of 12. Could have been 1, could have been 2, could have been 3, 4, 6 or 12. It couldn't be anything else. So this is interesting theory, and this leads into something called orders. So goes more into sort of like an Olympiad number theory sort of angle or group theory sort of angle. So we won't prove this. It's not that difficult, but it takes a while. It takes like some algebra, some calculation, and we won't use much of it. But this is just to show you the kind of things you can do with prime numbers. So like prime numbers are a bit more special when you're doing this stuff versus other types of numbers, right? We'll focus on a more calculation-based approach. We'll focus more on just like doing calculations. And so maybe we can try this example. So 2 power 29. So this has all the digits, 0 to 9, except a missing one. So there's one missing digit x, everything else is there. So what is the missing digit x? Can you find that? If you know the full number, then of course, I mean, you can just write the full number, 2 power 29. It's not that big to write, but can you find the missing digit without finding out the full number? Think about it. Wait, how 7?
Guess.
I mean, okay, 7 is a very natural guess, but.
In the tutor power, of course, even numbers will be there.
Oh no, wait, all the digits. I'm saying, so for example, 2 power 7, for example, is 128. Okay, so it's like a 1. If it's 2 power like 13, it's like 8192 or something, right? So it's like 1 and 9 are there. It's like these digits can be very random.
Yeah.
Yeah.
So, like we know that 1 comes, 2
Yeah.
comes, 3 comes.
Oh no, we just mean just this number, not everything till this point, but just this number, just this one number. So for example, we don't know it will have like 5 or 6, right? It may have like, but this number we know it has all the digits except one of them. There's only one digit missing, everything else is there. Yeah? So what is the missing digit and how do you find that missing digit? So, yeah? 5 because vibes, okay, fair. So not far. I mean, it's like, okay, if enough people guess, someone will get it, right? So it's also more like a probability question. Like, okay, how many people need to guess before there's like a 50% chance you get it, right? So that's also interesting. Yeah? Yeah, none of the answers are correct so far, so doing bad on the probability. Still wrong. No. Yeah, said like every number except the correct one. Like every number except the correct one. It's 4. So yeah. So
It ends with 4 though.
no, it ends with 4. You mean how so?
Well, I think I might have miscounted them. It ends with 2. I'm sorry. Yeah.
Ends with 2. Okay. So 2 power 4 cycles. 28 will give you like 8, and 2 power 29 will give you like 2, right? It'll end with 2. It'll end with 2. Yeah. That's a no worries. Yeah, no, so it's it's funny because that's the only missing one. So you got like all the other digits, Okay, but first we need to see how many digits this thing has, because there can be repetitions. If it's like very large number, then there can be repetitions. So 2 power 30 is like 2 power 10 cube, right? So this is like bigger than 10 power 9. So this has 9 digits. It doesn't have all 10, but it has at least 9 digits. Or 2 power 29 is between 10 power 8 and 10 power 9, right? Because this is not that much bigger. It's like 1.024 cube. Like we did this calculation yesterday, right? So it's not that much bigger. When you half it up, it'll be like between these two. So it has 9 digits, and there's only one missing one. So it has the rest of them, right?
Was it 9 digits if it lies with?
Oh yeah, it's like 10 and 100, so it's 2 digits, right? So it's like yeah, it's like 10 power 8 will whatever is the power of 10 plus 1 kind of thing. Yeah. So you look at this, and let's say these are the digits. A1 to A9 are the digits, right? If you look at the sum of all digits, it's the same as the remainder modulo 9, right? So this is an important fact. Like let's say your number n is A1 to AK. You can write this as A1 into 10 power k minus 1 plus A2 into 10 power k minus 2 plus AK at the end, right? Like you can write a number like this. If you take the whole number mod 9, 10 becomes 1. And so all these 10 powers go away, it just becomes sum of digits. So sum of digits is the same as the remainder mod 9, right? Because both will give you the same. So if I look at the sum here, a1 plus a9, it is the sum of everything from 0 to 9 minus the missing digit. So this is 0 plus 1 plus till plus 9 minus the missing x, right? And so this will be 45 minus x modulo 9, which is same as minus x mod 9. So I just need to find 2 power 29 mod 9, right? So let's find 2 power 29 mod 9. So minus x is congruent to 2 power 29 mod 9. 2 cube is minus 1, right? So 2 cube power 9 times 2 square, right? This is how we'll write this. And 2 cube is minus 1, so minus 1 power 9 into 4, so minus 4. So x is equal to 4. Yeah. And let me quickly use my calculator to find what the exact number is, and we can check if this is correct. 2 power 29. Yeah, it is 53680 something else. 6870912. That's the number. So it's missing a 4. And this is the missing 4. So it's a nice problem which mixes a lot of the ideas we saw yesterday as well. Like you bound it between powers of 10 to get the correct number of digits. Then you take the sum of digits using mod 9, and then you also find it using this powers modulo 9 property. So you use all three ideas together, and then you find a missing digit. Or you can just find a number directly. You can just like write the number. It's not that big of a number. You can calculate this, right? So it's not that big. Everybody good with this? Okay. Everybody good with this? That's good. Let's see what else. I'll leave the leap year question or the calendar question to you. You can figure it out. It's also similar type of logic, a bit easier than this. Okay. Maybe do you want to do one more like this just to get more feel for this type of modular arithmetic? Do you want to do one more question like this? Okay. So it's a little different. Okay, maybe I'll do one more like this and then we'll do something a little different. So, but the one more like this is a bit harder. So that's why I want to sort of switch here. This is a bit more difficult. So let's say my n is, I don't know if people have seen this. It's a famous sort of old one. This is my n. It's a huge number, an unbelievably big number, right? So this is n. S is the function from natural numbers to natural numbers, which takes little n to sum of digits n in base 10. So you write the n in decimal expression, you'll write 1, 2, 3. So for example, s of 1, 2, 3 is 1 plus 2 plus 3, which is 6, right? So it's just a sum of digits function. Find s of n. It's a horribly big number, like unbelievably big number. It's like 16,000 digits big number, you know, like 1 followed by 16,000 zeros. That's big. That's how big the number is. You find s of n to find the value of this over here. It's a very old IMO question, like 1970 something. I forget the year, but it's like 1917 IMO P4. So this is so it's problems are usually ordered. So P4 is the easiest problem in the day. There's P5, there's P6. So this is the sort of 1970 IMO problem there, and I forget the exact year, like maybe like 1976, 77, something like that. One of those years. So this is the kind of question they used to have in the IMO long ago. So just to give a feel. It's not too difficult from what we've already done. So what the theory we have done is enough to solve this question, but it takes a lot of thinking, it takes a lot of playing around to get there. And it's an interesting one, right? You're doing sum of digits, sum of digits, sum of digits. That's a strange function to do. Think about this. I'll give you guys some time to think about this because I think it is worth wondering, or at least think out loud about this. So whatever you're thinking, send me your strategy. Like what's your strategy for how you want to attack this? One strategy could be you want to look at this function s of s, right? Maybe you want to look at this function, see what kind of stuff it does. One strategy could be you want to look at n and figure out something about n, maybe some property about n. One strategy could be you want to figure out what s as a function does. So there's like 3 or 4 ideas you can start with, right? What is something you want to start with naturally? What is n? Okay, so n is just okay. How many digits does n have, for example? Like let's just understand the size of n first, right? So it's like 4, 4, 4, 4. How many digits, right? Well, it's like less than 10 power 4. So less than 16,000. What would that be? 17,000.
1777.
Okay. Digits. Okay. Not good. It's like okay, maybe just I'll make it a slightly better number just so I have like okay, it's worse, but at least it's a better looking number, right? Not good.
7777 because there will be also one on side.
Oh, it's like it'll be around 17,000, right? So like 4,000 and then around 16. So it's like order is correct roughly, right? So it's like this thing is less than 5,000 or like 4,500, and 4 times that is less than this. So this is good. Like this is a good enough bound. Like at most 18,000 digits. You know, not so bad. Not the end of the world. Okay. What happens when you take the sum of digits if you do this? For a number this big, how big the sum of digits should be? So how big? Well, at most all of these digits can be 9, right? Like the worst that can happen is all of these are 9. So S of n is less than 9 into 18,000. What is this? A 216? What's this? 162. Yeah, 162. Yeah, so it's like at most oh yeah, one more. Yeah, at most a 6-digit number, right? So at most a 6-digit number. This is S of n. So has at most 6 digits. It's a 6-digit number. That's quite a lot better than 18,000 digit number, right? It's like now it's a 6-digit number after just the first move.
And those 6 digits, the maximum it
And
could be.
after one more S of n.
Yeah. So S of n. This can have at most 6 digits, each at most 9, right? So at most 54. So it's a 2-digit number now. But it's not just any 2-digit number, it's like a number less equals 54 as well. So it's not like a very big 2-digit number either, right? Okay? S of n. Okay? This equals 18. Okay? 2-digit number, this equals 18. Okay? Can you improve this 18? Like, can you make this 18 better? I mean, 18 will require 99, right? Like that's the only way you get it. It can't be 18. You can't even like it has to be very, very small. Like the best you can get is like 4 and 9, right? So like 4 plus 9. So you can actually make it better. You make it like 13 or something. It's not that bad, right? Like at most 13 or something. Yeah, so this is less equal to 13 because among 1 to 54, the maximum number of digits you can get is 49, like 4 and 9, right? So like 13 is an improvement over 18. So it's a number between 0 and 18. 0 and 13, sorry. It's a number over here. How do you find it? There's like 13 numbers there. Like how do you find this?
Employ 13 people to give the exam.
Each of them answers, one of them will get it.
It will be not 13 because of course 4 4 above 4 4 this will be an even number at the end.
How do you know? Like you're adding digits, right? So it could be like 1, 2, 8, and then you have like a 1 at the end, right? So you don't really know anything about even odd. But that's it. It's an idea in the right spirit. Like you somehow want to have some more information about this number. So how is sum of digits connected to a number? What's the connection between sum of digits and a number? Mod 9, right? So n is same as S of n mod 9, which is same as S of n mod 9, and same as the number we want, S of n mod 9, right? and this is the number we want. Okay, number we want. Now we are still, what could happen, and this is a dangerous thing which can happen, is A is 2 mod 9, because then it could be 10, 2 or 11 and we don't know which one. So if it's 2 mod 9, we are in a bad position, right? If this n is 2 mod 9, then the answer could be 2 or 11 and we don't know, we have no way of knowing. But if the answer is like n is like 6 mod 9 or 8 mod 9, then it can't be 17 or it can't be like 15 because it's less than 13. Let's see what the value is then. It's 4, 4, 4, 4. So it's congruent to 4 plus 4 plus 4 is 16. 16 is 7. 7 power 4, 4, 4 mod 9, right? And now let's do 7. So 7 square is 49, which is 4. 7 cube is 28, which is 1. 7 cube is 1, right? So now you do 7 cube power, what's this modulo 3? 16, so it's 1. 3 into 4, 4, 4, 5. Sorry. 3 plus 1, yeah. And this is like this divided by 3. Yeah.
We could probably get that
Yeah.
number, sum of digits, go down to like 11 or something.
Yeah, no, you can probably get it down to 11, but you don't need to. Like now we are
Because
already.
when we had 162,000,
Yeah.
the mass it could be was just 99,000.
Yeah, no, we can probably have improved it more. Yeah, no, for sure. But it's like, okay, you don't need to improve anymore. Like if you were stuck, we would have had to improve, but now we are good, right? So this is 7 cube power this times 7. Sorry. So 7 cube power 443 by 3 times 7. That's 7 power 444. Yeah, so it's 7 mod 9. So answer is 7 mod 9. A is 7 mod 9 and A is between 0 and 13. It can only be 7. There's no other chance for A, it can only be 7. That's a very tricky thing to do, right? Like first you cut down from digits all the way down, and then you also use another piece of information. It's like 2 pieces of the puzzle and they give you the answer at the end. So that's kind of how you solve this one. I wanted to save this for a bit later because it's a bit more difficult than the next one. So next one will feel a bit easier. That's the saving grace, and it will feel a bit easier. But yeah, that's one of the ways of using this type of idea. Okay, and so any questions about the previous one? Like 444 power 444? Maybe one more 4. I'm not saying enough 4s, like there's more 4s in that somewhere. Okay, everybody comfortable with this? Everybody good with this? Okay. So now we can do something slight variation on this idea. So now we are not just going to do one type of mod. All the mods we are doing are by prime numbers so far, right? So like 13, 7, all the prime number mods. We'll try to do something slightly more interesting. So you might have seen puzzles like this. I have X number of coins, let's say. If I split this in 2 people, 1 is left. Split this in 3 people, 2 is left. Split this in 3 people, 4 people, 3 is left, and then so on, right? That's what I'm getting. So find the smallest possible number of coins I could have had. So maybe I'll do this. So I have X coins, and X is the smallest number with the following property. If I split this in a group of 2 people equally, 1 coin is left at the end. Split in a group of 3, 2 coins are left at the end. Split in a group of 4, 3 coins are left. Group of 5, 4 coins are left at the end. What's the smallest number X which I can have, which has all of these properties? So effectively I'm saying is X is 1 mod 2, 2 mod 3, 3 mod 4, 4 mod 5. Yeah. So what's the smallest number X which has all of these properties? 60? Hmm? 61, it's 60 is close, but 61 is on the wrong side. Because 61 modulo, what is it? Yeah? Yeah? 61 mod 5 is just 1, right? 59, exactly, 59. So if I do X plus 1, is 0 modulo 2, 3, 4, 5. So it's something is divisible by 2, 3, 4, 5. I'm doing plus 1, so 1 plus 1 is 2. 2 plus 1 3, 3 plus 1 4, 4 plus 1 5, right? So I'm something divisible by 2, 3, 4, 5 is divisible by 60. Just the LCM, right? 60 is the LCM for them, so it's divisible by 60. So X is at least 59, and 59 works. So 59 is the smallest value then, right? So that's how you solve these types of questions. But what if I had different values? So let's say I forget the 4 and I had like random stuff. I had like 1 mod 2, 2 mod 3, 3 mod 5 or something. Then becomes, now you can't do this plus 1 trick, right? Like there's no way of making all of these come together. So it's unclear how to solve these types of questions. Like it's not very clear how to do them. But I won't prove this or give a full algorithm because it's a complicated thing to write. But there's something called the, I don't know if this is the original name, maybe it's the modern name, the Chinese remainder theorem. So there is some theorem which lets you solve all these equations. What this says is that if I'm solving equations of the form P1, A2 mod P2, A n mod Pn, and Pi are prime numbers. More generally, they have to be pairwise co-prime, but that's a technical condition. For our purposes, they are all prime numbers. So they're all prime numbers, and I'm solving these equations. I can always solve them. There's always such an x. There is always a solution, and between 0 and P1 multiplied by till Pn, unique solution. There's a unique solution. So this is a pretty important theorem. It lets you solve all of these types of problems. I won't prove it, although proof is not very difficult. Proof is well within, like, takes like 10 more minutes to explain why this works. But it's very complicated. There's too much algebra to write out, so it's not that fun to write out. Like, you can look it up if you're interested. But this is the general idea, is that the point is that this can always be solved. Like, all such questions can be solved is all I wanted to point out. Like, you can do them, right? So with this in mind, all of this background, I'll give you a new question. You can think about that. Let's say n is the number 1, 2, 3, 8, 9, 10, 11, 12, 43, 44. I think 44. I don't know if there's 45. Let me check if there's 45. 44. I think it's only 44. Yeah, so this is your number n. You write all the numbers from 1 till 44. Find n mod 45. So find the value of n modulo 45. Yeah, one number with just 1, 2, 3, 4, all the way 8, 9, 10, all of these digits, right, till 44. So just one big number, so many digits, like 9 plus 44 minus 9 is like 35 into 2, like 79 digit number, like a 79 digit number. So it's a huge number, and then you have to find this modulo 45. And once we solve this, we'll go back to, let's say, the agent question with the agent who's watching someone. We'll go back to it, because then we'll have all the, you don't need all this theory. It's more like now you're comfortable with remainders, and so it's more, that's a much easier question than all of these, but it's sort of, you just have to be comfortable type of thing. But just think about how you do modulo 45, right? We have only seen modulo 9, modulo prime numbers. We've not really seen anything to do with this 45, right? So maybe you can split the 45, it's like 5 into 9, right? So maybe try solving it for 5 and 9 separately and see what happens. Just try doing it and see what happens, right? Yeah. So n is 4 mod 5. And n is, what is n mod 9? It's the sum of all digits. But doing sum of digits for like 1, 2, 1, 3 is on. Exactly. So when you're doing 1 plus 2, you can just do 12 instead. So you can just add all the numbers wholesale. You can just add all of them from 1 plus 2 till 44. Instead of doing like 1, 3, 1, 7 as 1 plus 3, 1 plus 7. Exactly. Exactly. Like for example, in this sum, what you were doing was till plus 9, and then for 1, 0, you'll make it 1, 0. Instead, you can make it 10. 1, 1, you can make it 11, because all these are same mod 9, right? So you're using mod 9 properties twice. So you end up getting this whole sum, and this is half of 44 into 45 is 0 mod 9, right? Because 45 is a multiple. So n is a multiple of 9, that is 4 mod 5. So maybe we'll try to do some algebra. N is of the form 9k, and 9k is congruent to 4 mod 5. Right? 9k is congruent to 4 mod 5. That's what we have, right? So 9k is what? Is minus k. 9k is just minus k, right? Because you have 10k, so you go minus k. And 4 is just minus 1. So k is just 1 mod 5, right? K is just 1 mod 5, right? So now you can write k as 5m plus 1. If you really want to do more algebra, you can write it this way, right? And you plug this back in. This is 45m plus 9. It's like 9 times this plus 9. So the remainder is just 9 now. It's like 45m plus something, so that 9 is the remainder now. And this is the general process of solving all these. It's like you can use this type of algebra to convert the variables enough times. Like if this was 5 into 9 into 7, you might have to use like 5m plus 1 modulo 7 is something else, and then find m in terms of L or something, like keep doing this algebra. But eventually you'll be able to find something which you can convert here. That's basically the process. The 9, so the answer is just 9 modulo 45. And yeah, you have to be a little careful with the, so this tricky stuff like this you have to be careful with, but yeah.
So can you also do an approach like if we see we divide it into a number like 1, 2, 3, 5, 6, 7, 8, 9,
Yeah.
the sum of that is 45.
Yeah.
Then we go from 10 to 19, we get 10 is 1,
Yeah.
11 is 2.
Yes, this also works, yeah. This,
So till, for
Every
every
multiple.
multiple 9 the sum is
yes,
45. So till
Yeah.
45 is 225.
Exactly.
We subtract 45, that's just
exactly. This also works, this is completely fine, yeah. Yeah, so any group of 9 multiples, like starting from 9t plus 1 till 9 of t plus 1. Between this, when you add, it's like all this is multiple of 9. Yes, that also works, yeah. Yeah, so it's like, everybody good with this? It's like thumbs up if you're good with this. Okay, so now we can go back to the agents problem. This was on the question paper. Question number 12 or what was it? This was 12, I think, yeah. Question number 12. So you have all of these agents from 1 to 1001, and agent number I, so everyone is watching someone and everyone is being watched by someone, right? So it's like everyone has one arrow going out and one arrow going in, so that sort of thing. So what do you expect in this structure where you have one arrow going out, one arrow going in? What do you expect will happen? So it doesn't have to be full circle. For example, it can be triangle and then a quadrilateral. Like it can happen like, oh, you split this into a bunch of these types of things, right?
This was like that one prisoner's riddle.
Yeah.
Yeah. So this is related. So this is, okay, you can have something like this, but the point is that, okay, because you have, if I is in the circle, if I is over here, I plus 1 is also here, right? That's the condition, that agent I is watching whoever is watching agent I plus 1. That's the condition, right? I watching agent watching I plus 1, watching agent I plus 1. So because of this condition, if I is inside one of the circles, I plus 1 is also inside the circle. So actually you can't have multiple bunch of these cycles, you'll only have one cycle, one big cycle with all of them. So you just have like one big cycle, 2, 3. So this is an important step. If you don't do that, then you can have like disjoint cycles, for example. You can have a cycle of 1, 2, 3, you can have a cycle of 4, 5, 6, 7, 8. You can have like disjoint, like if you don't have this particular step, you can have disjoint cycles. But this I and I plus 1 being in the same cycle forces all of them to be in the one cycle, right? Now, what is happening here? So let's say 1 goes to C plus 1, where C is just something we don't know about, right? So 1 is pointing to C plus 1, let's say. Then C plus 1 is watching whoever is watching C plus 2. Whoever is watching C plus 2, right? So this one goes to C plus 2. And then C plus 2 is watching 3, and 3 is watching C plus 3, and so on. Make sense? So 1 is watching C plus 1, where C is just some number we made up. If 1 is watching C plus 1 is watching whoever is watching C plus 2. And C plus 2 is watching 2 because 1 is watching whoever is watching 2. Right? So 1 is watching whoever is watching 2 implies C plus 1 is watching 2. Because we are saying 1 is watching C plus 1. C plus 1 is watching whoever is watching C plus 2. And C plus 1 is watching 2. So implies 2 is watching C plus 2. Make sense? So we keep building this chain. So I is watching C plus I. Yeah, I is watching C plus I, right? Now, in that sense, when you loop back to C plus 1 is watching C plus 1 plus C to C plus 1. But C plus 1 is watching 2. Make sense? So I is watching C plus I, but this is not a condition by itself. If you go overboard, like there's no such thing as, like if C is let's say 10 and your numbers till this, so 992 cannot be watching 1002 because there's no 1002, it loops back. So it's like this is modulo 1001, right? Because it's like afterwards you loop back in the cycle. Make sense? So because 992 cannot be watching 1002, like there's no 1002 person, right? So who's he watching then? It's like, oh, you do this modulo 1001 goes back to 1 if C is 10. If C is something else, it's something else. But the point is that every I is watching C plus I. You can establish this modulo 1001. So you can prove this just by going along the chain. You can use induction, many ways of proving this, right? So you end up proving this. But now C plus 1 was watching 2 and C plus 1 was watching C plus 1 plus C modulo 1001. So 2C plus 1 is equal to 2 modulo 1001, right? So 2C is equal to 1 modulo 1001. Still a bit tricky, like we don't know which C satisfies this, but we can make it 1 plus 1001, so 1002. And now we can take 2 common, right? So 1001 divides 2 times C minus 501. And 1001 has nothing to do with 2, so you can just cancel the 2, forget the 2. So C must be 501. So what you end up saying is that I is watching I plus 501 modulo 1001, right? And so 37 is watching 538. And this is very interesting because I is going to I plus 501. If you go again, I plus 501 is watching I plus 501 plus 501. This thing is just 1. So maybe I'll go to the next page. So we have shown that I is watching I plus 501. Who is watching I plus 501 plus 501 modulo 1001, which is just I plus 1. Right? And so this is actually what's happening. There's a cycle which goes by 501 plus and then does it again and reaches back to I plus 1. Yeah? You just?
I just took half.
It's half, yeah, exactly, half, for sure. Exactly. So it's like you expect, in some sense you expect whatever the gap is, the double of that gap is 1. So it's like half in some sense, right? And it's half in the modular arithmetic sense. So this is sort of the complete, like you can have the same idea, and if you notice this pattern then you can just solve the problem. So in the test we intended you to just notice the pattern, but here we want you to also understand why the proof works, right? The proof is that if all these cycles were disjoint, it was just like triangle this, like let's say you're splitting all of your vertices like this, all of these 1 to 1001 like this, then you can't make this argument, then this won't work. But because I and I plus 1 are both in every cycle, like in every such chain, I and I plus 1 are there, implies I plus 2 is there, implies I plus 3 is there and so on. So everything is there in a cycle. So all of this is one cycle. And once it is all one cycle, then you can use this argument of modular arithmetic remainders, right? So this was one of my favorite questions in the test because it's like, you can still have the correct feeling, correct intuition, and then solve the question. That's how we intended it. And then you can also dive deeper and learn about cycles and learn about modular arithmetic. So it's like, it serves 2 functions. It serves not just the function of intuition, but also the function of learning maths, right? So it's both functions. Any questions about this? Everybody good with this? All good? Just like thumbs up. If you have any questions, feel free to, because that's a tricky question over there. Right, so this. I don't know if you have more time for more of the questions today. There's like 3 more left. Maybe I'll give you one more about divisibility and you can think about this, right? So you've seen divisibility criteria for 2, 3, 5 and 9, right? Everybody knows these criteria, right? 11, the alternate digits you add, right? Do you know the criteria for 7, 13?
You were told it was way too complicated.
Way too complicated, okay? 101, okay? So all of them have the same idea. Like the idea for 9 is the idea which carries over for all of them. It's just that we say that in a way which is confusing, right? So all of them have the same idea. Let's see how. So what is the divisibility criteria trying to do? Let's say n is ak. Mod 9 is same as a1 plus ak because 10 power everything is 1 mod 9, right? So what is the divisibility criteria for 11? N mod 11. So if you have a1 into 10 power k minus 1, ak minus 1, 10 plus ak. Now 10 is minus 1 mod 11. 10 is minus 1 mod 11, right? So this one becomes minus ak minus 1. Next one, ak minus 2 becomes plus because 10 square, then minus, then plus, then minus, right? That's how you get the alternating sum. So this mod 11 alternating sum. Yeah. So that is a bit surprising. That should be a little surprising. The criteria just follows from the exact same idea that works for 9, works over here. In fact, it is not only that if 11 divides this alternating sum, 11 divides n, this alternating sum is the remainder when you divide it by 11. It's even stronger than the divisibility criteria, right? Make sense? Okay. So what about 7? Well, we want to find something such that 10 power that thing is 1 mod 7, right? Or even better, for example, for 11, let me give you a different criteria for 11 before we do 7. I'll give you a different divisibility criteria for 11. So if you want to check 5, 6 mod 11, if you want to check this, you add 56, 34 and 12 and check that modulo 11. Now there's no alternating sum. So this is same as this modulo 11. Why? Because you have this plus 100 times 34 and 100 is 1 mod 11. You have 12 times 10 power 4, which is again 1 mod 11. Right, so you can write this as 12 into 10 power 4, 34 into 10 square, plus 56. This is 1, this is 1. So it just becomes sum. You don't even need the alternating sum, you just have a plus now. So the criteria for 11 is just the same as the criteria for 9, but you take digits 2 at a time. So for 7, we want to find the smallest. So yeah, 10 power 3 is 1000. And 1001, so there's a good factorization. 1001 is 7 into 11 into 13. So this is minus 1, right? So 10 cube is minus 1 mod 7. 7. And so here's the cool thing, right? If I write a number like 1, 2, 3, 4, 5, 6, 7, 8, 9, modulo 7, now you can do 3-digit alternating sums. Minus 789, 456, minus 123. So you can do 3-digit alternating sums. That's the divisibility criteria for 7. It gives you the exact remainder. If your number was really big, if your number was like this, you can do digits of 6. You can split it into blocks of 6. Add those numbers. You don't even need the plus minus sign. You can just add all of them. That's the divisibility criteria for 7. Right, so now all these are the same idea. They're not different things. They're exactly the same idea. It's just like because it looks complicated to write, they tell you that it's a complicated thing, but it's the exact same idea as the others. In fact, for 13 you do the same thing, right? So 10 power 3 is minus 1. So 13 and 7 have the same divisibility criteria. They do like alternating negatives, 3-digit things. In fact, for 101, 10 square is minus 1. Right? So you actually do alternating 2-digit now. So let's say I want to check 1, 2, 3, 4, 5, 6, 7, 8 mod 101. I'll just do 78 minus 56, 34. I'll just check this. Yeah. Or if I wanted to, I can check this plus this. 1, 2, 3, 4 plus 5, 6, 7, 8 modulo 101. So all of these are the same criteria, is the same idea, and then you can solve any divisibility problem if you want this with mod 10, finding this. If you're curious, you can explore something about what happens when you do reciprocals. So look at the decimal expansion of 1 by 7. I think you get like 1428. And this has some relation to this stuff. There's like some connection between these two things. How many steps it takes before the decimal starts repeating has something to do with this order over here, the smallest thing over here. So there's some connections between these two ideas. And if you are curious, you can look into it afterwards. I won't spend too much time on it. But yeah, that's the discussion for today. I think we'll have like 105. So we'll resume tomorrow and we'll finish the rest of the problems, go a bit deeper into 1 or 2 of them. There's like some nice idea with inequalities and optimization. So I think both the red cards and blue cards problem, and the last one, the ABC, DEF. The factorial one I think is more divisibility, but the other two, I think, what was the other one? The ABCDEF. They lead to some discussion about discrete optimization. So you might have seen, like in calculus, you might have seen like continuous optimization, right? Like you take derivative and stuff. But with discrete things, it's not that simple. Like in discrete numbers, if you just have over integers, you can't take derivative over integers, right? Like so, it's you have to do something different there. So you'll have some discussion about discrete optimization. If you want, if you're interested, we can also discuss like more calculus-based optimization as well. We can do that tomorrow then, after finishing 15th, which is a divisibility question. Everybody good? Any questions? We'll end the stream then.